Aerodynamics for Naval Aviators. By H. H. Hurt, Jr. University of Southern California. Preface. The purpose of this textbook is to present the elements of applied aerodynamics and aeronautical engineering which relate directly to the problems of flying operations. All naval aviators possess a natural interest in the basic aerodynamic factors which affect the performance of all aircraft. Due to the increasing complexity of modern aircraft, this natural interest must be applied to develop a sound understanding of basic engineering principles and an appreciation of some of the more advanced problems of aerodynamics and engineering. The safety and effectiveness of flying operations will depend greatly on the understanding and appreciation of how and why an airplane flies. The principles of aerodynamics will provide the foundations for developing exacting and precise flying techniques and operational procedures. The content of this textbook has been arranged to provide as complete as possible a reference for all phases of flying in naval aviation. Hence, the text material is applicable to the problems of flight training, transition training, and general flying operations. The manner of presentation throughout the text has been designed to provide the elements of both theory and application, and will allow either directed or unassisted study. As a result, the text material will be applicable to supplement formal class lectures and briefings and provide reading material as a background for training and flying operations. Much of the specialized mathematical detail of aerodynamics has been omitted wherever it was considered unnecessary in the field of flying operations. Also, many of the basic assumptions and limitations of certain parts of aerodynamic theory have been omitted for the sake of simplicity and clarity of presentation. In order to contend with these specific shortcomings, the naval aviator should rely on the assistance of certain specially qualified individuals within naval aviation. For example, graduate aeronautical engineers, graduates of the Test Pilot Training School at the Naval Air Test Center, graduates of the Naval Aviation Safety Officers course, and technical representatives of the manufacturers are qualified to assist in interpreting and applying the more difficult parts of aerodynamics and aeronautical engineering. To be sure, the specialized qualifications of these individuals should be utilized wherever possible. The majority of aircraft accidents are due to some type of error of the pilot. This fact has been true in the past and, unfortunately, most probably will be true in the future. Each naval aviator should strive to arm himself with knowledge, training, and exacting, professional attitudes and techniques. The fundamentals of aerodynamics as presented in this text will provide the knowledge and background for safe and effective flying operations. The flight handbooks for the aircraft will provide the particular techniques, procedures, and operating data which are necessary for each aircraft. Diligent study and continuous training are necessary to develop the professional skills and techniques for successful flying operations. The author takes this opportunity to express appreciation to those who have assisted in the preparation of the manuscript. In particular, thanks are due to Mr. J. E. Fairchild for his assistance with the portions dealing with helicopter aerodynamics and roll coupling phenomena. Also, thanks are due to Mr. J. F. Detweiler and Mr. E. Dimitruk for their review of the text material. Hugh Harrison Hurt, Jr. August, 1959. University of Southern California, Los Angeles, California. Chapter 1. Basic Aerodynamics. In order to understand the characteristics of his aircraft and develop precision flying techniques, the naval aviator must be familiar with the fundamentals of aerodynamics. There are certain physical laws which describe the behavior of airflow and define the various aerodynamic forces and moments acting on a surface. These principles of aerodynamics provide the foundations for good, precise flying techniques. Wing and airfoil forces. Properties of the atmosphere. The aerodynamic forces and moments acting on a surface are due in great part to the properties of the air mass in which the surface is operating. The composition of the Earth's atmosphere by volume is approximately 78% nitrogen, 21% oxygen, and 1% water vapor, argon, carbon dioxide, etc. For the majority of all aerodynamic considerations, air is considered as a uniform mixture of these gases. The usual quantities used to define the properties of an air mass are as follows. Static pressure. The absolute static pressure of the air is a property of primary importance. The static pressure of the air at any altitude results from the mass of air supported above that level. At standard sea level conditions, the static pressure of the air is 2,116 pounds per square foot, or 14.7 psi, 29.92 inches of mercury, etc., and at 40,000 feet altitude, this static pressure decreases to approximately 19% of the sea level value. The shorthand notation for the ambient static pressure is lowercase p, and the standard sea level static pressure is given the subscript naught for 0 altitude, lowercase p naught. A more usual reference in aerodynamics and performance is the proportion of the ambient static pressure and the standard sea level static pressure. This static pressure ratio is assigned the shorthand notation of lowercase delta. Altitude pressure ratio equals ambient static pressure over standard sea level static pressure. Or lowercase delta equals lowercase p over lowercase p naught. Many items of gas turbine engine performance are directly related to some parameter involving the altitude pressure ratio. Temperature. The absolute temperature of the air is another important property. The ordinary temperature measurement by the centigrade scale has a datum at the freezing point of water, but absolute zero temperature is obtained at a temperature of -273 degrees centigrade. Thus, the standard sea level temperature of 15 degrees centigrade is an absolute temperature of 288 degrees. This scale of absolute temperature using the centigrade increments is the Kelvin scale, e.g., degrees Kelvin. The shorthand notation for the ambient air temperature is uppercase T, and the standard sea level air temperature of 288 Kelvin is signified by uppercase T naught. The more usual reference is the proportion of the ambient air temperature and the standard sea level air temperature. This temperature ratio is assigned the shorthand notation of lowercase theta. Temperature ratio equals ambient air temperature over standard sea level air temperature. Or lowercase theta equals uppercase T over uppercase T naught. Or lowercase theta equals degrees centigrade plus 273 divided by 288. Many items of compressibility effects and jet engine performance involve consideration of the temperature ratio. Density. The density of the air is a property of greatest importance in the study of aerodynamics. The density of air is simply the mass of air per cubic foot of volume and is a direct measure of the quantity of matter in each cubic foot of air. Air at standard sea level conditions weighs 0.0765 pounds per cubic foot and has a density of 0.002378 slugs per cubic foot. At an altitude of 40,000 feet, the air density is approximately 25% of the sea level value. The shorthand notation used for air density is lowercase rho, and the standard sea level air density is then lowercase rho naught. In many parts of aerodynamics, it is very convenient to consider the proportion of the ambient air density and standard sea level air density. This density ratio is assigned the shorthand notation of lowercase sigma. Density ratio equals ambient air density over standard sea level air density. Or lowercase sigma equals lowercase rho over lowercase rho naught. A general gas law defines the relationship of pressure, temperature, and density when there is no change of state or heat transfer. Simply stated, this would be density varies directly with pressure, inversely with temperature. Using the properties previously defined, density ratio equals pressure ratio over temperature ratio. Or lowercase rho over lowercase rho naught equals uppercase p over uppercase p naught times uppercase t naught over uppercase t. Or lowercase sigma equals lowercase delta over lowercase theta. This relationship has great application in aerodynamics and is quite fundamental and necessary in certain parts of airplane performance. Viscosity. The viscosity of the air is important in scale and friction effects. The coefficient of absolute viscosity is the proportion between the shearing stress and velocity gradient for a fluid flow. The viscosity of gases is unusual in that the viscosity is generally a function of temperature alone, and an increase in temperature increases the viscosity. The coefficient of absolute viscosity is assigned the shorthand notation lowercase mu. Since many parts of aerodynamics involve consideration of viscosity and density, a more usual form of viscosity measure is the proportion of the coefficient of absolute viscosity and density. This combination is termed the kinematic viscosity and is noted by lowercase nu. Kinematic viscosity equals the coefficient of absolute viscosity over density. Or lowercase nu equals lowercase mu over lowercase rho. The kinematic viscosity of air at standard sea level conditions is 0.000157 square feet per second. At an altitude of 40,000 feet, the kinematic viscosity is increased to 0.00050559 square feet per second. In order to provide a common denominator for comparison of various aircraft, a standard atmosphere has been adopted. The standard atmosphere actually represents the mean or average properties of the atmosphere. Figure 1.1 illustrates the variation of the most important properties of the air throughout the standard atmosphere. Notice that the lapse rate is constant in the troposphere, and the stratosphere begins with the isothermal region. Since all aircraft performance is compared and evaluated in the environment of the standard atmosphere, all of the aircraft instrumentation is calibrated for the standard atmosphere. Thus, certain corrections must apply to the instrumentation as well as the aircraft performance if the operating conditions do not fit the standard atmosphere. In order to properly account for the non-standard atmosphere, certain terms must be defined. Pressure altitude is the altitude in the standard atmosphere corresponding to a particular pressure. The aircraft altimeter is essentially a sensitive barometer, calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 inches of mercury, the altitude indicated is the pressure altitude, the altitude in the standard atmosphere corresponding to the sense pressure. Of course, this indicated pressure altitude may not be the actual height above sea level due to variations in temperature, lapse rate, atmospheric pressure, and possible errors in the sense pressure. The more appropriate term for correlating aerodynamic performance in the non-standard atmosphere is density altitude, the altitude in the standard atmosphere corresponding to a particular value of air density. The computation of density altitude must certainly involve consideration of pressure, pressure altitude, and temperature. Figure 1.6 illustrates the manner in which pressure altitude and temperature combine to produce a certain density altitude. This chart is quite standard in use and is usually included in the performance section of the flight handbook. Many subject areas of aerodynamics and aircraft performance will emphasize density altitude and temperature as the most important factors requiring consideration. Bernoulli's principle and subsonic airflow. All of the external aerodynamic forces on a surface are the result of air pressure or air friction. Friction effects are generally confined to a thin layer of air in the immediate vicinity of the surface, and friction forces are not the predominating aerodynamic forces. Therefore, the pressure forces created on an aerodynamic surface can be studied in a simple form which at first neglects the effect of friction and viscosity of the airflow. The most appropriate means of visualizing the effect of airflow and the resulting aerodynamic pressures is to study the fluid flow within a closed tube. Suppose a stream of air is flowing through the tube shown in figure 1.2. The airflow at station 1 in the tube has a certain velocity, static pressure, and density. As the airstream approaches the constriction at station 2, certain changes must take place. Since the airflow is enclosed within the tube, the mass flow at any point along the tube must be the same, and the velocity, pressure, or density must change to accommodate this continuity of flow. Bernoulli's equation. A distinguishing feature of subsonic airflow is that changes in pressure and velocity take place with small and negligible changes in density. For this reason, the study of subsonic airflow can be simplified by neglecting the variation of density in the flow and assuming the flow to be incompressible. Of course, at high flow speeds which approach the speed of sound, the flow must be considered as compressible and compressibility effects taken into account. However, if the flow through the tube of figure 1.2 is considered subsonic, the density of the airstream is essentially constant at all stations along the length. If the density of the flow remains constant, static pressure and velocity are the variable quantities. As the flow approaches the constriction of station 2, the velocity must increase to maintain the same mass flow. As the velocity increases, the static pressure will decrease, and the decrease in static pressure which accompanies the increase in velocity can be verified in two ways. 1. Newton's laws of motion state the requirement of an unbalanced force to produce an acceleration, velocity change. If the airstream experiences an increase in velocity approaching the constriction, there must be an unbalance of force to provide the acceleration. Since there is only air within the tube, the unbalance of force is provided by the static pressure at station 1 being greater than the static pressure at the constriction, station 2. 2. The total energy of the airstream in the tube is unchanged. However, the airstream energy may be in two forms. The airstream may have a potential energy which is related by the static pressure and a kinetic energy by virtue of mass and motion. As the total energy is unchanged, an increase in velocity, kinetic energy, will be accompanied by a decrease in static pressure, potential energy. This situation is analogous to a ball rolling along a smooth surface. As the ball rolls downhill, the potential energy due to position is exchanged for kinetic energy of motion. If friction were negligible, the change of potential energy would equal the change in kinetic energy. This is also the case for the airflow within the tube. The relationship of static pressure and velocity is maintained throughout the length of the tube. As the flow moves past the constriction toward station 3, the velocity decreases, and the static pressure increases. The Bernoulli equation for incompressible flow is most readily explained by accounting for the energy of the airflow within the tube. As the airstream has no energy added or subtracted at any point, the sum of the potential and kinetic energy must be constant. The kinetic energy of an object is found by Ke equals 1/2 mv squared, where Ke equals kinetic energy in foot-pounds, m equals mass in slugs, and v equals air velocity in feet per second. The kinetic energy of a cubic foot of air is Ke per cubic foot equals 1/2 lowercase rho v squared, where Ke per cubic foot equals kinetic energy per cubic foot, equivalent to pounds per square foot or PSF. Lowercase rho equals air density in slugs per cubic foot, and v equals air velocity in feet per second. If the potential energy is represented by the static pressure, lowercase p, the sum of the potential and kinetic energy is the total pressure of the airstream. H equals p plus 1/2 lowercase rho v squared, where H equals total pressure in pounds per square foot, sometimes referred to as head pressure. P equals static pressure in pounds per square foot. Lowercase rho equals density in slugs per cubic foot, and v equals velocity in feet per second. This equation is the Bernoulli equation for incompressible flow. It is important to appreciate that the term 1/2 lowercase rho v squared has the units of pressure, pounds per square foot. This term is one of the most important in all aerodynamics and appears so frequently that it is given the name dynamic pressure and the shorthand notation lowercase q. Lowercase q equals dynamic pressure in pounds per square foot, or 1/2 lowercase rho v squared. With this definition, it could be said that the sum of static and dynamic pressure in the flow tube remains constant. Figure 1.3 illustrates the variation of static, dynamic, and total pressure of air flowing through a closed tube. Note that the total pressure is constant throughout the length, and any change in dynamic pressure produces the same magnitude change in static pressure. The dynamic pressure of a free airstream is the one common denominator of all aerodynamic forces and moments. Dynamic pressure represents the kinetic energy of the free airstream and is a factor relating the capability for producing changes in static pressure on a surface. As defined, the dynamic pressure varies directly as the density and the square of the velocity. Typical values of dynamic pressure, lowercase q, are shown in Table 1-1 for various true airspeeds in the standard atmosphere. Notice that the dynamic pressure at some fixed velocity varies directly with the density ratio at any altitude. Also, appreciate the fact that at an altitude of 40,000 feet, where the density ratio, lowercase sigma, is 0.2462, it is necessary to have a true air velocity twice that at sea level in order to produce the same dynamic pressure. Airspeed measurement. If a symmetrically shaped object were placed in a moving airstream, the flow pattern typical of Figure 1.4 would result. The airstream at the very nose of the object would stagnate, and the relative flow velocity at this point would be 0. The airflow ahead of the object possesses some certain dynamic pressure and ambient static pressure. At the very nose of the object, the local velocity will drop to 0, and the airstream dynamic pressure will be converted into an increase in static pressure at the stagnation point. In other words, there will exist a static pressure at the stagnation point which is equal to the airstream total pressure, ambient static pressure plus dynamic pressure. Around the surface of the object, the airflow will divide, and the local velocity will increase from 0 at the stagnation point to some maximum on the sides of the object. If friction and viscosity effects are neglected, the surface airflow continues to the aft stagnation point where the local velocity is again 0. The important point of this example of aerodynamic flow is existence of the stagnation point. The change in airflow static pressure which takes place at the stagnation point is equal to the free stream dynamic pressure, lowercase q. The measurement of free stream dynamic pressure is fundamental to the indication of airspeed. In fact, airspeed indicators are simply pressure gauges which measure dynamic pressure related to various airspeeds. Typical airspeed measuring systems are illustrated in Figure 1.5. The pitot head has no internal flow velocity, and the pressure in the pitot tube is equal to the total pressure of the airstream. The purpose of the static ports is to sense the true static pressure of the free airstream. The total pressure and static pressure lines are attached to a differential pressure gauge, and the net pressure indicated is the dynamic pressure, lowercase q. The pressure gauge is then calibrated to indicate flight speed in the standard sea level air mass. For example, a dynamic pressure of 305 pounds per square foot would be realized at a sea level flight speed of 300 knots. Actually, there can be many conditions of flight where the airspeed indicator does not truly reflect the actual velocity through the air mass. The corrections that must be applied are many, and listed in sequence below. 1. The indicated airspeed, IAS, is the actual instrument indication for some given flight condition. Factors such as an altitude other than standard sea level, errors of the instrument and errors due to the installation, compressibility, etc., may create great variance between this instrument indication and the actual flight speed. 2. The calibrated airspeed, CAS, is the result of correcting IAS for errors of the instrument and errors due to position or location of the installation. The instrument error must be small by design of the equipment and is usually negligible in equipment which is properly maintained and cared for. The position error of the installation must be small in the range of airspeeds involving critical performance conditions. Position errors are most usually confined to the static source, in that the actual static pressure sensed at the static port may be different from the free airstream static pressure. When the aircraft is operated through a large range of angles of attack, the static pressure distribution varies quite greatly, and it becomes quite difficult to minimize the static source error. In most instances, a compensating group of static sources may be combined to reduce the position error. In order to appreciate the magnitude of this problem, at flight speed near 100 knots, a 0.05 psi position error is an airspeed error of 10 knots. A typical variation of airspeed system position error is illustrated in Figure 1.6. 3. The equivalent airspeed, EAS, is the result of correcting the calibrated airspeed for compressibility effects. At high flight speeds, the stagnation pressure recovered in the pitot tube is not representative of the airstream dynamic pressure, due to a magnification by compressibility. Compressibility of the airflow produces a stagnation pressure in the pitot which is greater than if the flow were incompressible. As a result, the airspeed indication is given an erroneous magnification. The standard airspeed indicator is calibrated to read correct when at standard sea level conditions, and thus has a compressibility correction appropriate for these conditions. However, when the aircraft is operating above standard sea level altitude, the inherent compensation is inadequate and additional correction must be applied. The subtractive corrections that must be applied to calibrated airspeed depend on pressure, altitude, and calibrated airspeed, and are shown on Figure 1.6 for the subsonic flight range. The equivalent airspeed, EAS, is the flight speed in the standard sea level air mass which would produce the same free stream dynamic pressure as the actual flight condition. 4. The true airspeed, TAS, results when the equivalent airspeed is corrected for density altitude. Since the airspeed indicator is calibrated for the dynamic pressures corresponding to airspeeds at standard sea level conditions, variations in air density must be accounted for. To relate equivalent airspeed and true airspeed requires consideration that the equivalent airspeed coupled with standard sea level density produces the same dynamic pressure as the true airspeed coupled with the actual air density of the flight condition. From this reasoning, it can be shown that TAS squared times lowercase rho equals EAS squared times lowercase rho naught. Or TAS equals EAS times the square root of lowercase rho naught over lowercase rho. Or TAS equals EAS times 1 over the square root of lowercase sigma. Where TAS equals true airspeed, EAS equals equivalent airspeed. lowercase rho equals actual air density. Lowercase rho naught equals standard sea level air density, and lowercase sigma equals altitude density ratio. Or lowercase rho over lowercase rho naught. The result shows that the TAS is a function of EAS and density altitude. Figure 1.6 shows a chart of density altitude as a function of pressure altitude and temperature. Each particular density altitude fixes the proportion between TAS and EAS. The use of a navigation computer requires setting appropriate values of pressure, altitude, and temperature on the scales, which then fixes the proportion between the scales of TAS and EAS, or TAS and CAS, when compressibility corrections are applicable. Thus, the airspeed indicator system measures dynamic pressure and will relate true flight velocity when instrument, position, compressibility, and density corrections are applied. These corrections are quite necessary for accurate determination of true airspeed and accurate navigation. Bernoulli's principle and the concepts of static, dynamic, and total pressure are the basis of aerodynamic fundamentals. The pressure distribution caused by the variation of local static and dynamic pressures on a surface is the source of the major aerodynamic forces and moment. Development of aerodynamic forces. The typical airflow patterns exemplify the relationship of static pressure and velocity defined by Bernoulli. Any object placed in an airstream will have the air to impact or stagnate at some point near the leading edge. The pressure at this point of stagnation will be an absolute, static pressure equal to the total pressure of the airstream. In other words, the static pressure at the stagnation point will be greater than the atmospheric pressure, by the amount of the dynamic pressure of the airstream. As the flow divides and proceeds around the object, the increases in local velocity produce decreases in static pressure. This procedure of flow is best illustrated by the flow patterns and pressure distributions of Figure 1.7. Streamline pattern and pressure distribution. The flow pattern of the cylinder of Figure 1.7 is characterized by the streamlines, which denote the local flow direction. Velocity distribution is noted by the streamline pattern, since the streamlines affect a boundary of flow, and the airflow between the streamlines is similar to flow in a closed tube. When the streamlines contract and are close together, high local velocities exist. When the streamlines expand and are far apart, low local velocities exist. At the forward stagnation point, the local velocity is zero, and the maximum positive pressure results. As the flow proceeds from the forward stagnation point, the velocity increases as shown by the change in streamlines. The local velocities reach a maximum at the upper and lower extremities, and a peak suction pressure is produced at these points on the cylinder. Note: positive pressures are pressures above atmospheric, and negative or suction pressures are less than atmospheric. As the flow continues aft from the peak suction pressure, the diverging streamlines indicate decreasing local velocities and increasing local pressures. If friction and compressibility effects are not considered, the velocity would decrease to zero at the aft stagnation point, and the full stagnation pressure would be recovered. The pressure distribution for the cylinder in perfect fluid flow would be symmetrical, and no net force, lift or drag, would result. Of course, the relationship between static pressure and velocity along the surface is defined by Bernoulli's equation. The flow pattern for the cylinder in an actual fluid demonstrates the effect of friction or viscosity. The viscosity of air produces a thin layer of retarded flow immediately adjacent to the surface. The energy expended in this boundary layer can alter the pressure distribution and destroy the symmetry of the pattern. The force unbalance caused by the change in pressure distribution creates a drag force, which is in addition to the drag due to skin friction. The streamline pattern for the symmetrical airfoil of Figure 1.7 again provides the basis for the velocity and pressure distribution. At the leading edge, the streamlines are widely diverged in the vicinity of the positive pressures. The maximum local velocities and suction, or negative, pressures exist where the streamlines are the closest together. One notable difference between the flow on the cylinder and the airfoil is that the maximum velocity and minimum pressure points on the airfoil do not necessarily occur at the point of maximum thickness. However, a similarity does exist in that the minimum pressure points correspond to the points where the streamlines are closest together, and this condition exists when the streamlines are forced to the greatest curvature. Generation of lift. An important phenomenon associated with the production of lift by an airfoil is the circulation imparted to the airstream. The best practical illustration of this phenomenon is shown in Figure 1.8 by the streamlines and pressure distributions existing on cylinders in an airstream. The cylinder without circulation has a symmetrical streamline pattern and a pressure distribution which creates no net lift. If the cylinder is given a clockwise rotation and induces a rotational or circulatory flow, a distinct change takes place in the streamline pattern and pressure distribution. The velocities due to the vortex of circulatory flow cause increased local velocity on the upper surface of the cylinder and decreased local velocity on the lower surface of the cylinder. Also, the circulatory flow produces an upwash immediately ahead and downwash immediately behind the cylinder, and both fore and aft stagnation points are lowered. The effect of the addition of circulatory flow is appreciated by the change in the pressure distribution on the cylinder. The increased local velocity on the upper surface causes an increase in upper surface suction, while the decreased local velocity on the lower surface causes a decrease in lower surface suction. As a result, the cylinder with circulation will produce a net lift. This mechanically induced circulation, called Magnus effect, illustrates the relationship between circulation and lift and is important to golfers, baseball and tennis players as well as pilots and aerodynamicists. The curvature of the flight path of a golf ball or baseball requires an unbalance of force which is created by rotation of the ball. The pitcher that can accurately control a powerful rotation will be quite a curveball artist. The golfer that cannot control the lateral motion of the club face striking the golf ball will impart an uncontrollable spin and have trouble with a hook or a slice. While a rotating cylinder can produce a net lift from the circulatory flow, the method is relatively inefficient and only serves to point out the relationship between lift and circulation. An airfoil is capable of producing lift with relatively high efficiency, and the process is illustrated in Figure 1.8. If a symmetrical airfoil is placed at zero angle of attack to the airstream, the streamline pattern and pressure distribution give evidence of zero lift. However, if the airfoil is given a positive angle of attack, changes occur in the streamline pattern and pressure distribution similar to changes caused by the addition of circulation to the cylinder. The positive angle of attack causes increased velocity on the upper surface with an increase in upper surface suction, while the decreased velocity on the lower surface causes a decrease in lower surface suction. Also, upwash is generated ahead of the airfoil, the forward stagnation point moves under the leading edge, and a downwash is evident aft of the airfoil. The pressure distribution on the airfoil now provides a net force perpendicular to the airstream, lift. The generation of lift by an airfoil is dependent upon the airfoil being able to create circulation in the airstream and develop the lifting pressure distribution on the surface. In all cases, the generated lift will be the net force caused by the distribution of pressure over the upper and lower surfaces of the airfoil. At low angles of attack, suction pressures usually will exist on both upper and lower surfaces, but the upper surface suction must be greater for positive lift. At high angles of attack near that for maximum lift, a positive pressure will exist on the lower surface, but this will account for approximately one-third the net lift. The effect of free stream density and velocity is a necessary consideration when studying the development of the various aerodynamic forces. Suppose that a particular shape of airfoil is fixed at a particular angle to the airstream. The relative velocity and pressure distribution will be determined by the shape of the airfoil and the angle to the airstream. The effect of varying the airfoil size, air density, and airspeed is shown in Figure 1.9. If the same airfoil shape is placed at the same angle to an airstream with twice as great a dynamic pressure, the magnitude of the pressure distribution will be twice as great, but the relative shape of the pressure distribution will be the same. With twice as great a pressure existing over the surface, all aerodynamic forces and moments will double. If a half-size airfoil is placed at the same angle to the original airstream, the magnitude of the pressure distribution is the same as the original airfoil, and again the relative shape of the pressure distribution is identical. The same pressure acting on the half-size surface would reduce all aerodynamic forces to one-half that of the original. This similarity of flow patterns means that the stagnation point occurs at the same place, the peak suction pressure occurs at the same place, and the actual magnitude of the aerodynamic forces and moments depends upon the airstream dynamic pressure and the surface area. This concept is extremely important when attempting to separate and analyze the most important factors affecting the development of aerodynamic forces. Airfoil terminology. Since the shape of an airfoil and the inclination to the airstream are so important in determining the pressure distribution, it is necessary to properly define the airfoil terminology. Figure 1.10 shows a typical airfoil and illustrates the various items of airfoil terminology. 1. The chord line is a straight line connecting the leading and trailing edges of the airfoil. 2. The chord is the characteristic dimension of the airfoil. 3. The mean camber line is a line drawn halfway between the upper and lower surfaces. Actually, the chord line connects the ends of the mean camber line. 4. The shape of the mean camber line is very important in determining the aerodynamic characteristics of an airfoil section. The maximum camber, displacement of the mean line from the chord line, and the location of the maximum camber help to define the shape of the mean camber line. These quantities are expressed as fractions or percent of the basic chord dimension. A typical low-speed airfoil may have a maximum camber of lowercase q% located 40% aft of the leading edge. 5. The thickness and thickness distribution of the profile are important properties of a section. The maximum thickness and location of maximum thickness define thickness and distribution of thickness. They are expressed as fractions or percent of the chord. A typical low-speed airfoil may have a maximum thickness of 12% located 30% aft of the leading edge. 6. The leading edge radius of the airfoil is the radius of curvature given the leading edge shape. It is the radius of the circle centered on a line tangent to the leading edge camber and connecting tangency points of upper and lower surfaces with the leading edge. Typical leading edge radii are 0, knife edge, to 1 or 2%. 7. The lift produced by an airfoil is the net force produced perpendicular to the relative wind. 8. The drag incurred by an airfoil is the net force produced parallel to the relative wind. 9. The angle of attack is the angle between the chord line and the relative wind. Angle of attack is given the shorthand notation lowercase alpha. Of course, it is important to differentiate between pitch attitude angle and angle of attack. Regardless of the condition of flight, the instantaneous flight path of the surface determines the direction of the oncoming relative wind, and the angle of attack is the angle between the instantaneous relative wind and the chord line. To respect the definition of angle of attack, visualize the flight path of the aircraft during a loop and appreciate that the relative wind is defined by the flight path at any point during the maneuver. Notice that the description of an airfoil profile is by dimensions which are fractions or percent of the basic chord dimension. Thus, when an airfoil profile is specified, a relative shape is described. Note: a numerical system of designating airfoil profiles originated by the National Advisory Committee for Aeronautics, NACA, is used to describe the main geometric features and certain aerodynamic properties. NACA Report Number 824 will provide the detail of this system. Aerodynamic force coefficient. The aerodynamic forces of lift and drag depend on the combined effect of many different variables. The important single variables could be 1. Airstream velocity. 2. Air density. 3. Shape or profile of the surface. 4. Angle of attack. 5. Surface area. 6. Compressibility effects. 7. Viscosity effects. If the effects of viscosity and compressibility are not of immediate importance, the remaining items can be combined for consideration. Since the major aerodynamic forces are the result of various pressures distributed on a surface, the surface area will be a major factor. Dynamic pressure of the airstream is another common denominator of aerodynamic forces and is a major factor since the magnitude of a pressure distribution depends on the source energy of the free stream. The remaining major factor is the relative pressure distribution existing on the surface. Of course, the velocity distribution and resulting pressure distribution are determined by the shape or profile of the surface and the angle of attack. Thus, any aerodynamic force can be represented as the product of three major factors: the surface area of the object, the dynamic pressure of the airstream, and the coefficient or index of force determined by the relative pressure distribution. This relationship is expressed by the following equation: F equals Cf times lowercase q times s, where F equals aerodynamic force in pounds, Cf equals coefficient of aerodynamic force, lowercase q equals dynamic pressure in pounds per square foot or 1/2 rho v squared, and s equals surface area in square feet. In order to fully appreciate the importance of the aerodynamic force coefficient, C sub F, the above equation is rearranged to alternate forms. Cf equals F over lowercase q times s. Or, Cf equals the quantity F over s over lowercase q. In this form, the aerodynamic force coefficient is appreciated as the aerodynamic force per surface area and dynamic pressure. In other words, the force coefficient is a dimensionless ratio between the average aerodynamic pressure, aerodynamic force per unit area, and the airstream dynamic pressure. All the aerodynamic forces of lift and drag are studied on this basis, the common denominator in each case being surface area and dynamic pressure. By such a definition, a lift coefficient would be the ratio between lift pressure and dynamic pressure. A drag coefficient would be the ratio between drag pressure and dynamic pressure. The use of the coefficient form of an aerodynamic force is necessary since the force coefficient is 1. An index of the aerodynamic force independent of area, density, and velocity. It is derived from the relative pressure and velocity distribution. 2. Influenced only by the shape of the surface and angle of attack since these factors determine the pressure distribution, and 3. An index which allows evaluation of the effects of compressibility and viscosity. Since the effects of area, density, and velocity are obviated by the coefficient form, compressibility and viscosity effects can be separated for study. The basic lift equation. Lift has been defined as the net force developed perpendicular to the relative wind. The aerodynamic force of lift on an airplane results from the generation of a pressure distribution on the wing. This lift force is described by the following equation. L equals capital C L times lowercase q times s, where L equals lift in pounds. Capital C L equals lift coefficient. Lowercase q equals dynamic pressure in pounds per square foot and s equals wing surface area in square feet. The lift coefficient used in this equation is the ratio of the lift pressure and dynamic pressure and is a function of the shape of the wing and angle of attack. If the lift coefficient of a conventional airplane wing planform were plotted versus angle of attack, the result would be typical of the graph of figure 1.11. Since the effects of speed, density, area, weight, altitude, etc., are eliminated by the coefficient form, an indication of the true lift capability is obtained. Each angle of attack produces a particular lift coefficient since the angle of attack is the controlling factor in the pressure distribution. Lift coefficient increases with angle of attack up to the maximum lift coefficient, capital CL max, and as angle of attack is increased beyond the maximum lift angle, the airflow is unable to adhere to the upper surface. The airflow then separates from the upper surface and stall occurs. Interpretation of the lift equation. Several important relationships are derived from study of the basic lift equation and the typical wing lift curve. One important fact to be appreciated is that the airplane shown in figure 1.11 stalls at the same angle of attack regardless of weight, dynamic pressure, bank angle, etc. Of course, the stall speed of the aircraft will be affected by weight, bank angle, and other factors since the product of dynamic pressure, wing area, and lift coefficient must produce the required lift. A rearrangement of the basic lift equation defines this relationship. L equals capital C L times lowercase q times s. Using lowercase q equals lowercase sigma times v squared over 295, with v in knots true airspeed. L equals capital C L times lowercase sigma times v squared over 295 times s. Solving for v equals 17.2 times the square root of L divided by capital C L times lowercase sigma times s. Since the stall speed is the minimum flying speed necessary to sustain flight, the lift coefficient must be the maximum, capital CL max. Suppose that the airplane shown in figure 1.11 has the following properties. Weight equals 14,250 pounds. Wing area equals 280 square feet. Capital CL max equals 1.5. If the airplane is flown in steady, level flight at sea level with lift equal to weight, the stall speed would be Vs equals 17.2 times the square root of W over capital CL max times lowercase sigma times s, where Vs equals stall speed in knots true airspeed. W equals weight in pounds. Lift equals weight. Vs equals 17.2 times the square root of 14,250 divided by 1.5 times 1.000 times 280 equals 100 knots. Thus, a sea-level airspeed, or EAS, of 100 knots would provide the dynamic pressure necessary at maximum lift to produce 14,250 pounds of lift. If the airplane were operated at a higher weight, a higher dynamic pressure would be required to furnish the greater lift, and a higher stall speed would result. If the airplane were placed in a steep turn, the greater lift required in the turn would increase the stall speed. If the airplane were flown at a higher density altitude, the TAS at stall would increase. However, one factor common to each of these conditions is that the angle of attack at CL max is the same. It is important to realize that stall warning devices must sense angle of attack, lowercase alpha, or pressure distribution, related to CL. Another important fact related by the basic lift equation and lift curve is variation of angle of attack and lift coefficient with airspeed. Suppose that the example airplane is flown in steady, wing 1 EVOL flight at various airspeeds with lift equal to the weight. It is obvious that an increase in airspeed above the stall speed will require a corresponding decrease in lift coefficient and angle of attack to maintain steady, lift equal weight flight. The exact relationship of lift coefficient and airspeed is evolved from the basic lift equation assuming constant lift, equal to weight, and equivalent airspeeds. CL over CL max equals the quantity Vs over V squared. The example airplane was specified to have weight equals 14,250 pounds. CL max equals 1.5. Vs equals 100 knots EAS. Note that for the conditions of steady flight, each airspeed requires a specific angle of attack and lift coefficient. This fact provides a fundamental concept of flying technique. Angle of attack is the primary control of airspeed in steady flight. Of course, the control stick or wheel allows the pilot to control the angle of attack and, thus, control the airspeed in steady flight. In the same sense, the throttle controls the output of the power plant and allows the pilot to control rate of climb and descent at various airspeeds. The real believers of these concepts are professional instrument pilots, LSOs, and glider pilots. The glider pilot, or flame-out enthusiast, has no recourse but to control airspeed by angle of attack and accept whatever rate of descent is incurred at the various airspeeds. The LSO must become quite proficient at judging the flight path and angle of attack of the airplane in the pattern. The more complete visual reference field available to the LSO allows him to judge the angle of attack of the airplane more accurately than the pilot. When the airplane approaches the LSO, the precise judgment of airspeed is by the angle of attack rather than the rate of closure. If the LSO sees the airplane on the desired flight path, but with too low an angle of attack, the airspeed is too high. If the angle of attack is too high, the airspeed is too low, and the airplane is approaching the stall. The mirror landing system coupled with an angle of attack indicator is an obvious refinement. The mirror indicates the desired flight path, and the angle of attack indicator allows precision control of the airspeed. The accomplished instrument pilot is the devotee of attitude, flying technique, his creed being attitude plus power equals performance. During a GCA approach, the professional instrument pilot controls airspeed with stick, angle of attack, and rate of descent with power adjustment. Maneuvering flight and certain transient conditions of flight tend to complicate the relationship of angle of attack and airspeed. However, the majority of flight and certainly the most critical regimes of flight, takeoff, approach, and landing, are conducted in essentially steady flight conditions. Airfoil lift characteristics. Airfoil section properties differ from wing or airplane properties because of the effect of the planform. Actually, the wing may have various airfoil sections from root to tip with taper, twist, sweep, and local flow components in a spanwise direction. The resulting aerodynamic properties of the wing are determined by the action of each section along the span, and the three-dimensional flow. Airfoil section properties are derived from the basic shape or profile in two-dimensional flow, and the force coefficients are given a notation of lowercase letters. For example, a wing or airplane lift coefficient is uppercase CL, while an airfoil section lift coefficient is termed lowercase cl. Also, wing angle of attack is lowercase alpha while section angle of attack is differentiated by the use of lowercase alpha naught. The study of section properties allows an objective consideration of the effects of camber, thickness, etc. The lift characteristics of 5 illustrative airfoil sections are shown in Figure 1.12. The section lift coefficient, lowercase cl, is plotted versus section angle of attack, lowercase alpha naught, for 5 standard NACA airfoil profiles. One characteristic feature of all airfoil sections is that the slope of the various lift curves is essentially the same. At low lift coefficients, the section lift coefficient increases approximately 0.1 for each degree increase in angle of attack. For each of the airfoils shown, a 5-degree change in angle of attack would produce an approximate 0.5 change in lift coefficient. Evidently, lift curve slope is not a factor important in the selection of an airfoil. An important lift property affected by the airfoil shape is the section maximum lift coefficient, lowercase cl max. The effect of airfoil shape on lowercase cl max can be appreciated by comparison of the lift curves for the 5 airfoils of Figure 1.12. The NACA airfoils 63-006, 63-009, and 63-012 are symmetrical sections of a basic thickness distribution, but maximum thicknesses of 6, 9, and 12% respectively. The effect of thickness on lowercase cl max is obvious from an inspection of these curves. The 12% section has a lowercase cl max approximately 70% greater than the 6% thick section. In addition, the thicker airfoils have greater benefit from the use of various high lift devices. The effect of camber is illustrated by the lift curves of the NACA 4412 and 63-412 sections. The NACA 4412 section is a 12% thick airfoil which has 4% maximum camber located at 40% of the chord. The NACA 63-412 airfoil has the same thickness and thickness distribution as the 63-012, but camber added to give a design lift coefficient, lowercase cl for minimum section drag, of 0.4. The lift curves for these two airfoils show that camber has a beneficial effect on lowercase cl max. An additional effect of camber is the change in zero lift angle. While the symmetrical sections have zero lift at zero angle of attack, the sections with positive camber have negative angles for zero lift. The importance of maximum lift coefficient is obvious. If the maximum lift coefficient is high, the stall speed will be low. However, the high thickness and camber necessary for high section maximum lift coefficients may produce low critical Mach numbers and large twisting moments at high speed. In other words, a high maximum lift coefficient is just one of the many features desired of an airfoil section. Drag characteristics. Drag is the net aerodynamic force parallel to the relative wind, and its source is the pressure distribution and skin friction on the surface. Large, thick bluff bodies in an airstream show a predominance of form drag due to the unbalanced pressure distribution. However, streamlined bodies with smooth contours show a predominance of drag due to skin friction. In a fashion similar to other aerodynamic forces, drag forces may be considered in the form of a coefficient which is independent of dynamic pressure and surface area. The basic drag equation is as follows. D equals capital C dQs, where D equals drag in pounds. Capital CD equals drag coefficient. Lowercase q equals dynamic pressure in pounds per square foot. Or, lowercase sigma times v squared over 295, with v in knots true air speed. And S equals wing surface area in square feet. The force of drag is shown as the product of dynamic pressure, surface area, and drag coefficient, capital CD. The drag coefficient in this equation is similar to any other aerodynamic force coefficient. It is the ratio of drag pressure to dynamic pressure. If the drag coefficient of a conventional airplane were plotted versus angle of attack, the result would be typical of the graph shown in Figure 1.13. At low angles of attack, the drag coefficient is low and small changes in angle of attack create only slight changes in drag coefficient. At higher angles of attack the drag coefficient is much greater and small changes in angle of attack cause significant changes in drag. As stall occurs, a large increase in drag takes place. A factor more important in airplane performance considerations is the lift-to-drag ratio, L over D. With the lift and drag data available for the airplane, the proportions of CL and CD can be calculated for each specific angle of attack. The resulting plot of lift-to-drag ratio with angle of attack shows that L/D increases to some maximum then decreases at the higher lift coefficients and angles of attack. Note that the maximum lift-to-drag ratio, L/D max, occurs at one specific angle of attack and lift coefficient. If the airplane is operated in steady flight at L/D max, the total drag is at a minimum. Any angle of attack lower or higher than that for L/D max reduces the lift-to-drag ratio and consequently increases the total drag for a given airplane lift. The airplane depicted by the curves of Figure 1.13 has a maximum lift-to-drag ratio of 12.5 at an angle of attack of 6 degrees. Suppose this airplane is operated in steady flight at a gross weight of 12,500 pounds. If flown at the airspeed and angle of attack corresponding to L/D max, the drag would be 1,000 pounds. Any higher or lower airspeed would produce a drag greater than 1,000 pounds. Of course, this same airplane could be operated at higher or lower gross weights, and the same maximum lift-to-drag ratio of 12.5 could be obtained at the same angle of attack of 6 degrees. However, a change in gross weight would require a change in airspeed to support the new weight at the same lift coefficient and angle of attack. The configuration of an airplane has a great effect on the lift-to-drag ratio. Typical values of L/D max are listed for various types of airplanes. Type of airplane: high-performance sailplane. L/D max 25 to 40. Type of airplane: typical patrol or transport. L/D max 12 to 20. Type of airplane: high-performance bomber. L/D max 20 to 25. Type of airplane: propeller-powered trainer. L/D max 10 to 15. Type of airplane: jet trainer. L/D max 14 to 16. Type of airplane: transonic fighter or attack. L/D max 10 to 13. Type of airplane: supersonic fighter or attack. L/D max 4 to 9, subsonic. While the high-performance sailplane may have extremely high lift-to-drag ratios, such an aircraft has no real economic or tactical purpose. The supersonic fighter may have seemingly low lift-to-drag ratios in subsonic flight, but the airplane configurations required for supersonic flight, and high L/Ds at high Mach numbers, precipitate this situation. Many important items of airplane performance are obtained in flight at L/D max. Typical performance conditions which occur at L/D max are: maximum endurance of jet-powered airplanes, maximum range of propeller-driven airplanes, maximum climb angle for jet-powered airplanes, maximum power-off glide range, jet or prop. The most immediately interesting of these items is the power-off glide range of an airplane. By examining the forces acting on an airplane during a glide, it can be shown that the glide ratio is numerically equal to the lift-to-drag ratio. For example, if the airplane in a glide has an L/D of 15, each mile of altitude is traded for 15 miles of horizontal distance. Such a fact implies that the airplane should be flown at L/D max to obtain the greatest glide distance. An unbelievable feature of gliding performance is the effect of airplane gross weight. Since the maximum lift-to-drag ratio of a given airplane is an intrinsic property of the aerodynamic configuration, gross weight will not affect the gliding performance. If a typical jet trainer has an L/D max of 15, the aircraft can obtain a maximum of 15 miles horizontal distance for each mile of altitude. This would be true of this particular airplane at any gross weight if the airplane is flown at the angle of attack for L/D max. Of course, the gross weight would affect the glide airspeed necessary for this particular angle of attack, but the glide ratio would be unaffected. Airfoil drag characteristics. The total drag of an airplane is composed of the drags of the individual components, and the forces caused by interference between these components. The drag of an airplane configuration must include the various drags due to lift, form, friction, interference, leakage, etc. To appreciate the factors which affect the drag of an airplane configuration, it is most logical to consider the factors which affect the drag of airfoil sections. In order to allow an objective consideration of the effects of thickness, camber, etc., the properties of two-dimensional sections must be studied. Airfoil section properties are derived from the basic profile in two-dimensional flow and are provided the lowercase shorthand notation to distinguish them from wing or airplane properties, e.g., wing or airplane drag coefficient is capital CD, while airfoil section drag coefficient is lowercase cd. The drag characteristics of three illustrative airfoil sections are shown in Figure 1.14. The section drag coefficient, lowercase cd, is plotted versus the section lift coefficient, lowercase cl. The drag on the airfoil section is composed of pressure drag and skin friction. When the airfoil is at low lift coefficients, the drag due to skin friction predominates. The drag curve for a conventional airfoil tends to be quite shallow in this region since there is very little variation of skin friction with angle of attack. When the airfoil is at high lift coefficients, form or pressure drag predominates, and the drag coefficient varies rapidly with lift coefficient. The NACA 0006 is a thin symmetrical profile which has a maximum thickness of 6% located at 30% of the chord. This section shows a typical variation of lowercase cd and lowercase cl. The NACA 4412 section is a 12% thick airfoil with 4% maximum camber at 40% chord. When this section is compared with the NACA 0006 section, the effect of camber can be appreciated. At low lift coefficients, the thin, symmetrical section has much lower drag. However, at lift coefficients above 0.5, the thicker, cambered section has the lower drag. Thus, proper camber and thickness can improve the lift-to-drag ratio of the section. The NACA 63-412 is a cambered 12% thick airfoil of the laminar flow type. This airfoil is shaped to produce a design lift coefficient of 0.4. Notice that the drag curve of this airfoil has distinct aberrations with very low drag coefficients near the lift coefficient of 0.4. This airfoil profile has its camber and thickness distributed to produce very low uniform velocity on the forward surface, minimum pressure point well aft, at this lift coefficient. The resulting pressure and velocity distribution enhance extensive laminar flow in the boundary layer and greatly reduce the skin friction drag. The benefit of the laminar flow is appreciated by comparing the minimum drag of this airfoil with an airfoil which has 1/2 the maximum thickness, the NACA 0006. The choice of an airfoil section will depend on the consideration of many different factors. While the lowercase cl max of the section is an important quality, a more appropriate factor for consideration is the maximum lift coefficient of the section when various high lift devices are applied. Trailing edge flaps and leading edge high lift devices are applied to increase the lowercase cl max for low speed performance. Thus, an appropriate factor for comparison is the ratio of section drag coefficient to section maximum lift coefficient with flaps lowercase cd over lowercase cl max sub f. When this quantity is corrected for compressibility, a preliminary selection of an airfoil section is possible. The airfoil having the lowest value of lowercase cd over lowercase cl max sub f at the design flight condition, endurance, range, high speed, etc., will create the least section drag for a given design stall speed. Flight at high lift conditions. It is frequently stated that the career naval aviator spends more than half his life below 1,000 feet and 100 knots. Regardless of the implications of such a statement, the thought does connote the relationship of minimum flying speeds and carrier aviation. Only in naval aviation is there such importance assigned to precision control of the aircraft at high lift conditions. Safe operation in carrier aviation demands precision control of the airplane at high lift conditions. The aerodynamic lift characteristics of an airplane are portrayed by the curve of lift coefficient versus angle of attack. Such a curve is illustrated in Figure 1.15 for a specific airplane in the clean and flap down configurations. A given aerodynamic configuration experiences increases in lift coefficient with increases in angle of attack until the maximum lift coefficient is obtained. A further increase in angle of attack produces stall, and the lift coefficient then decreases. Since the maximum lift coefficient corresponds to the minimum speed available in flight, it is an important point of reference. The stall speed of the aircraft in level flight is related by the equation Vs equals 17.2 times the square root of capital W over capital CL max times lowercase sigma times capital S, where Vs equals stall speed in knots true airspeed. W equals gross weight in pounds. Capital C Lmax equals airplane maximum lift coefficient. Lowercase sigma equals altitude density ratio. And capital S equals wing area in square feet. This equation illustrates the effect on stall speed of weight and wing area, or wing loading, W over S, maximum lift coefficient, and altitude. If the stall speed is desired in EAS, the density ratio will be that for sea level, lowercase sigma, equals 1.000. Effective weight. Modern configurations of airplanes are characterized by a large percent of the maximum gross weight being fuel. Hence, the gross weight and stall speed of the airplane can vary considerably throughout the flight. The effect of only weight on stall speed can be expressed by a modified form of the stall speed equation where density ratio, capital C Lmax, and wing area are held constant. Vs sub 2 over Vs sub 1 equals the square root of capital W sub 2 over capital W sub 1. Where Vs sub 1 equals stall speed corresponding to some gross weight, W sub 1. And Vs sub 2 equals stall speed corresponding to a different gross weight, W sub 2. As an illustration of this equation, assume that a particular airplane has a stall speed of 100 knots at a gross weight of 10,000 pounds. The stall speeds of this same airplane at other gross weights would be: gross weight, 10,000 pounds. Stall speed, 100 knots EAS. Gross weight, 11,000 pounds. Stall speed, 100 times the square root of 11,000 over 10,000, equals 105 knots EAS. Gross weight, 12,000 pounds. Stall speed, 110 knots EAS. Gross weight, 14,000 pounds. Stall speed, 120 knots EAS. Gross weight, 9,000 pounds. Stall speed, 95 knots EAS. Gross weight, 100 pounds. Stall speed, 90 knots EAS. Figure 1.15 illustrates the effect of weight on stall speed on a percentage basis and will be valid for any airplane. Many specific conditions of flight are accomplished at certain fixed angles of attack and lift coefficients. The effect of weight on a percentage basis on the speeds for any specific lift coefficient and angle of attack is identical. Note that at small variations of weight, a rule of thumb may express the effect of weight on stall speed. A 2% change in weight causes a 1% change in stall speed. Effective maneuvering flight. Turning flight and maneuvers produce an effect on stall speed which is similar to the effect of weight. Inspection of the chart on Figure 1.16 shows the forces acting on an airplane in a steady turn. Any steady turn requires that the vertical component of lift be equal to weight of the airplane, and the horizontal component of lift be equal to the centrifugal force. Thus, the aircraft in a steady turn develops a lift greater than weight and experiences increased stall speeds. Trigonometric relationships allow determination of the effect of bank angle on stall speed and load factor. The load factor, lowercase n, is the proportion between lift and weight and is determined by lowercase n equals L over W, or lowercase n equals 1 over cosine lowercase phi, where lowercase n equals load factor or G, and cosine lowercase phi equals cosine of the bank angle, lowercase phi. Typical values of load factor determined by this relationship are lowercase phi equals 0 degrees. Lowercase n equals 1.00. Lowercase phi equals 15 degrees. Lowercase n equals 1.035. Lowercase phi equals 30 degrees. Lowercase n equals 1.154. Lowercase phi equals 45 degrees. Lowercase n equals 1.414. Lowercase phi equals 60 degrees. Lowercase n equals 2.000. Lowercase phi equals 75.5 degrees. Lowercase n equals 4.00. The stall speed in a turn can be determined by Vs sub phi equals Vs times the square root of lowercase n, where Vs sub phi equals stall speed at some bank angle, lowercase phi, Vs equals stall speed for wing level, lift equals weight flight, and n equals load factor corresponding to the bank angle. The percent increase in stall speed in a turn is shown on figure L.16. Since this chart is predicated on a steady turn and constant CL max, the figures are valid for any airplane. The chart shows that no appreciable change in load factor or stall speed occurs at bank angles less than 30 degrees. Above 45 degrees of bank, the increase in load factor and stall speed is quite rapid. This fact emphasizes the need for avoiding steep turns at low airspeeds, a flight condition common to stall spin accidents. Effect of high lift devices. The primary purpose of high lift devices, flaps, slots, slats, etc., is to increase the CL max of the airplane and reduce the stall speed. The takeoff and landing speeds are consequently reduced. The effect of a typical high lift device is shown by the airplane lift curves of figure 1.15 and is summarized here. Configuration: clean, flaps up. CL max, 1.5. Lowercase alpha for CL max, 20 degrees. Configuration: flaps down. CL max, 2.0. Lowercase alpha for CL max, 18.5 degrees. The principal effect of the extension of flaps is to increase the CL max and reduce the angle of attack for any given lift coefficient. The increase in CL max afforded by flap deflection reduces the stall speed in a certain proportion, the effect described by the equation. VSF equals Vs times the square root of CLm over CLmf, where VSF equals stall speed with flaps down, Vs equals stall speed without flaps, CLm equals maximum lift coefficient of the clean configuration, CLmf equals maximum lift coefficient with flaps down. For example, assume the airplane described by the lift curves of figure 1.15 has a stall speed of 100 knots at the landing weight in the clean configuration. If the flaps are lowered, the reduced stall speed is reduced to VSF equals 100 times the square root of 1.5 over 2.0. Or VSF equals 86.5 knots. Thus, with the higher lift coefficient available, less dynamic pressure is required to provide the necessary lift. Because of the stated variation of stall speed with CL max, large changes in CL max are necessary to produce significant changes in stall speed. This effect is illustrated by the graph in figure 1.16, and certain typical values are shown below. Percent increase in CL max, 2. Percent reduction in stall speed, 1. Percent increase in CL max, 10. Percent reduction in stall speed, 5. Percent increase in CL max, 50. Percent reduction in stall speed, 18. Percent increase in CL max, 100. Percent reduction in stall speed, 29. Percent increase in CL max, 300. Percent reduction in stall speed, 50. The contribution of the high lift devices must be considerable to cause a large reduction in stall speed. The most elaborate combination of flaps, slots, slats, and boundary layer control throughout the span of the wing would be required to increase CL max by 300%. A common case is that of a typical propeller-driven transport which experiences a 70% increase in CL max by full flap deflection. A typical single-engine jet fighter with a thin swept wing obtains a 20% increase in CL max by full flap deflection. Thin airfoil sections with sweepback impose distinct limitations on the effectiveness of flaps, and the 20% increase in CL max by flaps is a typical if not high value for such a configuration. One factor common to maximum lift condition is the angle of attack and pressure distribution. The maximum lift coefficient of a particular wing configuration is obtained at one angle of attack and one pressure distribution. Weight, bank angle, load factor, density, altitude, and airspeed have no direct effect on the stall angle of attack. This fact is sufficient justification for the use of angle of attack indicators and stall warning devices which sense pressure distribution on the wing. During flight maneuvers, landing, approach, takeoff, turns, etc., the airplane will stall if the critical angle of attack is exceeded. The airspeed at which stall occurs will be determined by weight, load factor, and altitude, but the stall angle of attack is unaffected. At any particular altitude, the indicated stall speed is a function of weight and load factor. An increase in altitude will produce a decrease in density and increase the true airspeed at stall. Also, an increase in altitude will alter compressibility and viscosity effects and, generally speaking, cause the induced stall speed to increase. This particular consideration is usually significant only above altitudes of 20,000 feet. Recovery from stall involves a very simple concept. Since stall is precipitated by an excessive angle of attack, the angle of attack must be decreased. This is a fundamental principle which is common to any airplane. An airplane may be designed to be stall-proof simply by reducing the effectiveness of the elevators. If the elevators are not powerful enough to hold the airplane to high angles of attack, the airplane cannot be stalled in any condition of flight. Such a requirement for a tactical military airplane would seriously reduce performance. High lift coefficients near the maximum are required for high maneuverability and low landing and takeoff speeds. Hence, the naval aviator must appreciate the effect of the many variables affecting the stall speed and regard attitude flying, angle of attack indicators, and stall warning devices as techniques which allow more precise control of the airplane at high lift conditions. High lift devices. There are many different types of high lift devices used to increase the maximum lift coefficient for low-speed flight. The high lift devices applied to the trailing edge of a section consist of a flap which is usually 15 to 25% of the chord. The deflection of a flap produces the effect of a large amount of camber added well aft on the chord. The principal types of flaps are shown applied to a basic section of airfoil. The effect of a 30-degree deflection of a 25% chord flap is shown on the lift and drag curves of figure 1.17. The plane flap shown in figure 1.17 is a simple hinged portion of the trailing edge. The effect of the camber added well aft on the chord causes a significant increase in lowercase CL max. In addition, the zero lift angle changes to a more negative value, and the drag increases greatly. The split flap shown in figure 1.17 consists of a plate deflected from the lower surface of the section and produces a slightly greater change in lowercase CL max than the plane flap. However, a much larger change in drag results from the great turbulent wake produced by this type of flap. The greater drag may not be such a disadvantage when it is realized that it may be advantageous to accomplish steeper landing approaches over obstacles or require higher power from the engine during approach, to minimize engine acceleration time for wave-off. The slotted flap is similar to the plane flap, but the gap between the main section and flap leading edge is given specific contours. High-energy air from the lower surface is ducted to the flap upper surface. The high-energy air from the slot accelerates the upper surface boundary layer and delays airflow separation to some higher lift coefficient. The slotted flap can cause much greater increases in lowercase CL max than the plane or split flap, and section drags are much lower. The Fowler flap arrangement is similar to the slotted flap. The difference is that the deflected flap segment is moved aft along a set of tracks which increases the chord and affects an increase in wing area. The Fowler flap is characterized by large increases in lowercase CL max with minimum changes in drag. One additional factor requiring consideration in a comparison of flap types is the aerodynamic twisting moments caused by the flap. Positive camber produces a nose-down twisting moment, especially great when large camber is used well aft on the chord. An obvious implication is that flaps are not practical on a flying wing or tailless airplane. The deflection of a flap causes large nose-down moments which create important twisting loads on the structure and pitching moments that must be controlled with the horizontal tail. Unfortunately, the flap types producing the greatest increases in lowercase CL max usually cause the greatest twisting moments. The Fowler flap causes the greatest change in twisting moment while the split flap causes the least. This factor, along with mechanical complexity of the installation, may complicate the choice of a flap configuration. The effectiveness of flaps on a wing configuration depends on many different factors. One important factor is the amount of the wing area affected by the flaps. Since a certain amount of the span is reserved for ailerons, the actual wing maximum lift properties will be less than that of the flapped two-dimensional section. If the basic wing has a low thickness, any type of flap will be less effective than on a wing of greater thickness. Sweepback of the wing can cause an additional significant reduction in the effectiveness of flaps. High lift devices applied to the leading edge of a section consist of slots, slats, and small amounts of local camber. The fixed slot in a wing conducts flow of high-energy air into the boundary layer on the upper surface and delays airflow separation to some higher angle of attack and lift coefficient. Since the slot alone affects no change in camber, the higher maximum lift coefficient will be obtained at a higher angle of attack, i.e., the slot simply delays stall to a higher angle of attack. An automatic slot arrangement consists of a leading edge segment, slat, which is free to move on tracks. At low angles of attack, the slat is held flush against the leading edge by the high positive local pressures. When the section is at high angles of attack, the high local suction pressures at the leading edge create a chordwise force forward to actuate the slat. The slot formed then allows the section to continue to a higher angle of attack and produce a lowercase cl max greater than that of the basic section. The effect of a fixed slot on the lift characteristics is shown in Figure 1.18. Slots and slats can produce significant increases in lowercase cl max, but the increased angle of attack for maximum lift can be a disadvantage. If slots were the only high lift device on the wing, the high takeoff and landing angles of attack may complicate the design of the landing gear. For this reason, slots or slats are usually used in conjunction with flaps, since the flaps provide reduction in the maximum lift angle of attack. The use of a slot has two important advantages. There is only a negligible change in the pitching moment due to the slot and no significant change in section drag at low angles of attack. In fact, the slotted section will have less drag than the basic section near the maximum lift angle for the basic section. The slot-slat device finds great application in modern airplane configurations. The tailless airplane configuration can utilize only the high lift devices which have negligible effects on the pitching moments. The slot and slat are often used to increase the lowercase cl max in high-speed flight when compressibility effects are considerable. The small change in twisting moment is a favorable feature for any high-lift device to be used at high speed. Leading-edge high-lift devices are more effective on the highly swept wing than trailing-edge flaps, since slats are quite powerful in controlling the flow pattern. Small amounts of local camber added to the leading edge as a high-lift device is most effective on wings of very low thickness and sharp leading edges. Most usually, the slope of the leading edge high lift device is used to control the spanwise lift distribution on the wing. Boundary layer control devices are additional means of increasing the maximum lift coefficient of a section. The thin layer of airflow adjacent to the surface of an airfoil shows reduced local velocities from the effect of skin friction. When at high angles of attack, this boundary layer on the upper surface tends to stagnate and come to a stop. If this happens, the airflow will separate from the surface and stall occurs. Boundary layer control for high lift applications features various devices to maintain high velocity in the boundary layer to allay separation of the airflow. This control of the boundary layer kinetic energy can be accomplished in two ways. One method is the application of suction through ports to draw off low energy boundary layer air and replace it with high velocity air from outside the boundary layer. The effect of surface suction boundary layer control on lift characteristics is typified by Figure 1.18. Increasing surface suction produces greater maximum lift coefficients which occur at higher angles of attack. The effect is similar to that of a slot because the slot is essentially a boundary layer control device ducting high energy air to the upper surface. Another method of boundary layer control is accomplished by injecting a high-speed jet of air into the boundary layer. This method produces essentially the same results as the suction method and is the more practical installation. The suction type BLC requires the installation of a separate pump, while the blown BLC system can utilize the high pressure source of a jet engine compressor. The typical installation of a high pressure BLC system would be the augmentation of a deflected flap. Since any boundary layer control tends to increase the angle of attack for maximum lift, it is important to combine the boundary layer control with flaps, since the flap deflection tends to reduce the angle of attack for maximum lift. Operation of high lift devices. The management of the high lift devices on an airplane is an important factor in flying operations. The devices which are actuated automatically, such as automatic slats and slots, are usually of little concern and cause little complication, since relatively small changes in drag and pitching moments take place. However, the flaps must be properly managed by the pilot to take advantage of the capability of such a device. To illustrate a few principles of flap management, Figure 1.19 presents the lift and drag curves of a typical airplane in the clean and flap down configurations. In order to appreciate some of the factors involved in flap management, assume that the airplane has just taken off, and the flaps are extended. The pilot should not completely retract the flaps until the airplane has sufficient speed. If the flaps are retracted prematurely at insufficient airspeed, maximum lift coefficient of the clean configuration may not be able to support the airplane, and the airplane will sink or stall. Of course, this same factor must be considered for intermediate flap positions between fully retracted and fully extended. Assume that the airplane is allowed to gain speed and reduce the flight lift coefficient to the point of flap retraction indicated on Figure 1.19. As the configuration is altered from the cluttered to the clean configuration, three important changes take place. 1. The reduction in camber by flap retraction changes the wing pitching moment and, for the majority of airplanes, requires RETRMing to balance the nose-up moment change. Some airplanes feature automatic RETRMing, which is programmed with flap deflection. 2. The retraction of flaps shown on Figure 1.19 causes a reduction of drag coefficient at that lift coefficient. This drag reduction improves the acceleration of the airplane. 3. The retraction of flaps requires an increase in angle of attack to maintain the same lift coefficient. Thus, if airplane acceleration is low through the flap retraction speed range, angle of attack must be increased to prevent the airplane from sinking. This situation is typical after takeoff when gross weight, density, altitude, and temperature are high. However, some aircraft have such high acceleration through the flap retraction speed that the rapid gain in airspeed requires much less noticeable attitude change. When the flaps are lowered for landing, essentially the same items must be considered. Extending the flaps will cause these changes to take place. 1. Lowering the flaps requires RETRMing to balance the nose-down moment change. 2. The increase in drag requires a higher power setting to maintain airspeed and altitude. 3. The angle of attack required to produce the same lift coefficient is less, e.g., flap extension tends to cause the airplane to balloon. An additional factor which must be considered when rapidly accelerating after takeoff, or when lowering the flaps for landing, is the limit airspeed for flap extension. Excessive airspeeds in the flap down configuration may cause structural damage. In many aircraft, the effect of intermediate flap deflection is of primary importance in certain critical operating conditions. Small initial deflections of the flap cause noticeable changes in CL max without large changes in drag coefficient. This feature is especially true of the airplane equipped with slotted or Fowler flaps, refer to Figure 1.17. Large flap deflections past 30 to 35 degrees do not create the same rate of change of CL max, but do cause greater changes in CD. A fact true of most airplanes is that the first 50% of flap deflection causes more than half of the total change in CL max, and the last 50% of flap deflection causes more than half of the total change in CD. The effect of power on the stall speed of an airplane is determined by many factors. The most important factors affecting this relationship are power plant type, prop or jet, thrust-to-weight ratio, and inclination of the thrust vector at maximum lift. The effect of the propeller is illustrated in Figure 1.20. The slipstream velocity behind the propeller is different from the freestream velocity depending on the thrust developed. Thus, when the propeller-driven airplane is at low airspeeds and high power, the dynamic pressure in the shaded area can be much greater than the free stream, and this causes considerably greater lift than at zero thrust. At high power conditions, the induced flow also causes an effect similar to boundary layer control and increases the maximum lift angle of attack. The typical 4-engine propeller-driven airplane may have 60 to 80% of the wing area affected by the induced flow, and power effects on stall speeds may be considerable. Also, the lift of the airplane at a given angle of attack and airspeed will be greatly affected. Suppose the airplane shown is in the process of flaring to land from a power-on approach. If there is a sharp, sudden reduction of power, the airplane may drop suddenly because of the reduced lift. The typical jet aircraft does not experience the induced flow velocities encountered in propeller-driven airplanes, thus, the only significant factor is the vertical component of thrust. Since this vertical component contributes to supporting the airplane, less aerodynamic lift is required to hold the airplane in flight. If the thrust is small, and the thrust inclination is slight at maximum lift angle, only negligible changes in stall speed will result. On the other hand, if the thrust is very great and is given a large inclination at maximum lift angle, the effect on stall speed can be very large. One important relationship remains: since there is very little induced flow from the jet, the angle of attack at stall is essentially the same power on or power off. Development of aerodynamic pitching moments. The distribution of pressure over a surface is the source of the aerodynamic moments as well as the aerodynamic forces. A typical example of this fact is the pressure distribution acting on the cambered airfoil of Figure 1.21. The upper surface has pressures distributed which produce the upper surface lift, the lower surface has pressures distributed which produce the lower surface lift. Of course, the net lift produced by the airfoil is the difference between the lifts on the upper and lower surfaces. The point along the chord where the distributed lift is effectively concentrated is termed the center of pressure, CP. The center of pressure is essentially the center of gravity of the distributed lift pressure, and the location of the CP is a function of camber and section lift coefficient. Another aerodynamic reference point is the aerodynamic center, AC. The aerodynamic center is defined as the point along the chord where all changes in lift effectively take place. To visualize the existence of such a point, notice the change in pressure distribution with angle of attack for the symmetrical airfoil of Figure 1.21. When at zero lift, the upper and lower surface lifts are equal and located at the same point. With an increase in angle of attack, the upper surface lift increases while the lower surface lift decreases. The change of lift has taken place with no change in the center of pressure, a characteristic of symmetrical airfoils. Next, consider the cambered airfoil of Figure 1.21 at zero lift. To produce zero lift, the upper and lower surface lifts must be equal. One difference noted from the symmetrical airfoil is that the upper and lower surface lifts are not opposite one another. While no net lift exists on the airfoil, the couple produced by the upper and lower surface lifts creates a nose-down moment. As the angle of attack is increased, the upper surface lift increases while the lower surface lift decreases. While a change in lift has taken place, no change in moment takes place about the point where the lift change occurs. Since the moment about the aerodynamic center is the product of a force, lift at the CP, and a lever arm, distance from CP to AC, an increase in lift moves the center of pressure toward the aerodynamic center. It should be noted that the symmetrical airfoil at zero lift has no pitching moment about the aerodynamic center because the upper and lower surface lifts act along the same vertical line. An increase in lift on the symmetrical airfoil produces no change in this situation, and the center of pressure remains fixed at the aerodynamic center. The location of the aerodynamic center of an airfoil is not affected by camber, thickness, and angle of attack. In fact, two-dimensional incompressible airfoil theory will predict the aerodynamic center at the 25% chord point for any airfoil regardless of camber, thickness, and angle of attack. Actual airfoils, which are subject to real fluid flow, may not have the lift due to angle of attack concentrated at the exact 25% chord point. However, the actual location of the aerodynamic center for various sections is rarely forward of 23% or aft of 27% chord point. The moment about the aerodynamic center has its source in the relative pressure distribution and requires application of the coefficient form of expression for proper evaluation. The moment about the aerodynamic center is expressed by the following equation. Capital M sub AC equals capital M sub A C times lowercase q times capital S times lowercase c, where capital M sub AC equals moment about the aerodynamic center, AC, in foot-pounds, capital C M sub AC equals coefficient of moment about the AC, lowercase q, equals dynamic pressure in pounds per square foot, capital S equals wing area in square feet, and lowercase c equals chord in feet. The moment coefficient used in this equation is the dimensionless ratio of the moment pressure to dynamic pressure moment. Capital C M sub AC equals capital M sub A C over lowercase q times capital S times lowercase c, and is a function of the shape of the airfoil mean camber line. Figure 1.22 shows the moment coefficient, lowercase c M sub AC, versus lift coefficient for several representative sections. The sign convention applied to moment coefficients is that the nose-up moment is positive. The NACA 0009 airfoil is a symmetrical section of 9% maximum thickness. Since the mean line of this airfoil has no camber, the coefficient of moment about the aerodynamic center is 0, i.e., the CP is at the AC. The departure from 0 cm sub AC occurs only as the airfoil approaches maximum lift, and the stall produces a moment change in the negative, nose-down, direction. The NACA 4412 and 63-412 sections have noticeable positive camber which cause relatively large moments about the aerodynamic center. Notice that for each section shown in figure 1.22, cm sub AC is constant for all lift coefficients less than cl max. The NACA 23012 airfoil is a very efficient conventional section which has been used on many airplanes. One of the features of the section is a relatively high cl max with only a small cm sub AC. The pitching moment coefficients for this section are shown on figure 1.22 along with the effect of various type flaps added to the basic section. Large amounts of camber applied well aft on the chord cause large negative moment coefficients. This fact is illustrated by the large negative moment coefficients produced by the 30 degrees deflection of a 25% chord flap. The cm sub AC is a quantity determined by the shape of the mean camber line. Symmetrical airfoils have 0 cm sub AC, and the CP remains at the AC in unstalled flight. The airfoil with positive camber will have a negative cm sub AC, which means the CP is behind the AC. Since the cm sub AC is constant in unstalled flight, a certain relationship between lift coefficient and center of pressure can be evolved. An example of this relationship is shown in figure 1.22 for the NACA 63-412 airfoil by a plot of CP versus cl. Note that at low lift coefficients, the center of pressure is well aft, even past the trailing edge, and an increase in cl moves the CP forward toward the AC. The CP approaches the AC as a limit, but as stall occurs, the drop in suction near the leading edge causes the CP to move aft. Of course, if the airfoil has negative camber, or a strongly reflex trailing edge, the moment about the aerodynamic center will be positive. In this case, the location of the aerodynamic center will be unchanged and will remain at the quarter chord position. The aerodynamic center is the point on the chord where the coefficients of moment are constant, the point where all changes in lift take place. The aerodynamic center is an extremely important aerodynamic reference point, and the most direct application is to the longitudinal stability of an airplane. To simplify the problem, assume that the airplane is a tailless or flying wing type. In order for this type of airplane to have longitudinal stability, the center of gravity must be ahead of the aerodynamic center. This very necessary feature can be visualized from the illustrations of figure 1.23. If the two symmetrical airfoils are subject to an upgust, an increase in lift will take place at the AC. If the CG is ahead of the AC, the change in lift creates a nose-down moment about the CG which tends to return the airfoil to the equilibrium angle of attack. This stable, weathercocking tendency to return to equilibrium is a very necessary feature in any airplane. If the CG is aft of the AC, the change in lift due to the upgust takes place at the AC and creates a nose-up moment about the AC. This nose-up moment tends to displace the airplane farther from the equilibrium and is unstable. The airplane is similar to a ball balanced on a peak. Hence, to have a stable airplane, the CG must be located ahead of the airplane AC. An additional requirement of stability is that the airplane must stabilize and be trimmed for flight at positive lift. When the CG is located ahead of AC, the weight acting at the CG is supported by the lift developed by the section. Negative camber is required to produce the positive moment about the aerodynamic center which brings about equilibrium to balance at positive lift. Supersonic flow produces important changes in the aerodynamic characteristics of sections. The aerodynamic center of airfoils in subsonic flow is located at the 25% chord point. As the airfoil is subject to supersonic flow, the aerodynamic center changes to the 50% chord point. Thus, the airplane in transonic flight can experience large changes in longitudinal stability because of the large changes in the position of the aerodynamic center. Friction effects. Because the air has viscosity, air will encounter resistance to flow over a surface. The viscous nature of airflow reduces the local velocities on a surface and accounts for the drag of skin friction. The retardation of air particles due to viscosity is greatest immediately adjacent to the surface. At the very surface of an object, the air particles are slowed to a relative velocity of near zero. Above this area, other particles experience successively smaller retardation until finally, at some distance above surface, the local velocity reaches the full value of the airstream above the surface. This layer of air over the surface, which shows local retardation of airflow from viscosity, is termed the boundary layer. The characteristics of this boundary layer are illustrated in Figure 1.24 with the flow of air over a smooth flat plate. The beginning flow on a smooth surface gives evidence of a very thin boundary layer with the flow occurring in smooth laminations. The boundary layer flow near the leading edge is similar to layers or laminations of air sliding smoothly over one another, and the obvious term for this type of flow is the laminar boundary layer. This smooth laminar flow exists without the air particles moving from a given elevation. As the flow continues back from the leading edge, friction forces in the boundary layer continue to dissipate the energy of the airstream, and the laminar boundary layer increases in thickness with distance from the leading edge. After some distance back from the leading edge, the laminar boundary layer begins an oscillatory disturbance which is unstable. A waviness occurs in the laminar boundary layer which ultimately grows larger and more severe and destroys the smooth laminar flow. Thus, a transition takes place in which the laminar boundary layer decays into a turbulent boundary layer. The same sort of transition can be noticed in the smoke from a cigarette in still air. At first, the smoke ribbon is smooth and laminar, then develops a definite waviness, and decays into a random turbulent smoke pattern. As soon as the transition to the turbulent boundary layer takes place, the boundary layer thickens and grows at a more rapid rate. The small-scale, turbulent flow within the boundary layer should not be confused with the large-scale turbulence associated with airflow separation. The flow in the turbulent boundary layer allows the air particles to travel from one layer to another, producing an energy exchange. However, some small laminar flow continues to exist in the very lower levels of the turbulent boundary layer and is referred to as the laminar sublayer. The turbulence which exists in the turbulent boundary layer allows determination of the point of transition by several means. Since the turbulent boundary layer transfers heat more easily than the laminar layer, frost, water, and oil films will be removed more rapidly from the area aft of the transition point. Also, a small probe may be attached to a stethoscope and positioned at various points along a surface. When the probe is in the laminar area, a low hiss will be heard. When the probe is in the turbulent area, a sharp crackling will be audible. In order to compare the characteristics of the laminar and turbulent boundary layers, the velocity profiles, the variation of boundary layer velocity with height above the surface, should be compared under conditions which could produce either laminar or turbulent flow. The typical laminar and turbulent profiles are shown in Figure 1.24. The velocity profile of the turbulent boundary layer shows a much sharper initial change of velocity, but a greater height, or boundary layer thickness, required to reach the free stream velocity. As a result of these differences, a comparison will show. 1. The turbulent boundary layer has a fuller velocity profile and has higher local velocities immediately adjacent to the surface. The turbulent boundary layer has higher kinetic energy in the airflow next to the surface. 2. At the surface, the laminar boundary layer has the less rapid change of velocity with distance above the plate. Since the shearing stress is proportional to the velocity gradient, the lower velocity gradient of the laminar boundary layer is evidence of a lower friction drag on the surface. If the conditions of flow were such that either a turbulent or a laminar boundary layer could exist, the laminar skin friction would be about 1/3 that for turbulent flow. The low friction drag of the laminar boundary layer makes it quite desirable. However, the transition tends to take place in a natural fashion and limits the extensive development of the laminar boundary layer. Reynolds number. Whether a laminar or turbulent boundary layer exists depends on the combined effects of velocity, viscosity, distance from the leading edge, density, etc. The effect of the most important factors is combined in a dimensionless parameter called Reynolds number, Rn. The Reynolds number is a dimensionless ratio which portrays the relative magnitude of dynamic and viscous forces in the flow. Rn equals Vx over nu, where Rn equals Reynolds number, dimensionless, V equals velocity in feet per second, x, equals, distance from leading edge in feet, and, lowercase nu, equals, kinematic viscosity in square feet per second. While the actual magnitude of the Reynolds number has no physical significance, the quantity is used as an index to predict and correlate various phenomena of viscous fluid flow. When the Rn is low, viscous or friction forces predominate. When the Rn is high, dynamic or inertia forces predominate. The effect of the variables in the equation for Reynolds number should be understood. The Rn varies directly with velocity and distance back from the leading edge and inversely with kinematic viscosity. High Rns are obtained with large chord surfaces, high velocities, and low altitude. Low Rns result from small chord surfaces, low velocities, and high altitudes producing high values for kinematic viscosity. The most direct use of Reynolds number is the indexing or correlating the skin friction drag of a surface. Figure 1.25 illustrates the variation of the friction drag of a smooth, flat plate with a Reynolds number which is based on the length or chord of the plate. The graph shows separate lines of drag coefficient if the flow should be entirely laminar or entirely turbulent. The two curves for laminar and turbulent friction drag illustrate the relative magnitude of friction drag coefficient if either type of boundary layer could exist. The drag coefficients for either laminar or turbulent flow decrease with increasing Rn since the velocity gradient decreases as the boundary layer thickens. If the surface of the plate is smooth, and the original airstream has no turbulence, the plate at low Reynolds numbers will exist with pure laminar flow. When the Rn is increased to approximately 530,000, transition occurs on the plate, and the flow is partly turbulent. Once transition takes place, the drag coefficient of the plate increases from the laminar curve to the turbulent curve. As the Rn approaches very high values, 20 to 50 million, the drag curve of the plate approaches and nearly equals the values for the turbulent curve. At such high Rn, the boundary layer is predominantly turbulent with very little laminar flow. The transition point is very close to the leading edge. While the smooth, flat plate is not exactly representative of the typical airfoil, basic fluid friction phenomena are illustrated. At Rn less than 500,000, the boundary layer will be entirely laminar unless there is extreme surface roughness or turbulence induced in the airstream. Reynolds numbers between 1 and 5 million produce boundary layer flow which is partly laminar and partly turbulent. At Rn above 10 million, the boundary layer characteristics are predominantly turbulent. In order to obtain low drag sections, the transition from laminar to turbulent must be delayed so that a greater portion of the surface will be influenced by the laminar boundary layer. The conventional, low-speed airfoil shapes are characterized by minimum pressure points very close to the leading edge. Since high local velocities enhance early transition, very little surface is covered by the laminar boundary layer. A comparison of two 9% thick symmetrical airfoils is presented in Figure 1.25. One section is the conventional NACA 0009 section, which has a minimum pressure point at approximately 10% chord at zero lift. The other section is the NACA 66-009, which has a minimum pressure point at approximately 60% chord at zero lift. The lower local velocities at the leading edge, and the favorable pressure gradient of the NACA 66-009 delay the transition to some point farther aft on the chord. The subsequent reduction in friction drag at the low angles of attack accounts for the drag bucket shown on the graphs of lowercase cd and lowercase cl for these sections. Of course, the advantages of the laminar flow airfoil are apparent only for the smooth airfoil since surface roughness or waviness may preclude extensive development of a laminar boundary layer. Airflow separation. The character of the boundary layer on an aerodynamic surface is greatly influenced by the pressure gradient. In order to study this effect, the pressure distribution of a cylinder in a perfect fluid is repeated in Figure 1.26. The airflows depict a local velocity of 0 at the forward stagnation point and a maximum local velocity at the extreme surface. The airflow moves from the high positive pressure to the minimum pressure point, a favorable pressure gradient, high to low. As the air moves from the extreme surface aft, the local velocity decreases to 0 at the aft stagnation point. The static pressure increases from the minimum, or maximum suction, to the high positive pressure at the aft stagnation point, an adverse pressure gradient, low to high. The action of the pressure gradient is such that the favorable pressure gradient assists the boundary layer while the adverse pressure gradient impedes the flow of the boundary layer. The effect of an adverse pressure gradient is illustrated by the segment XY of figure 1.26. A corollary of the skin friction drag is the continual reduction of boundary layer energy as flow continues aft on a surface. The velocity profiles of the boundary layer are shown on segment XY of figure 1.26. In the area of adverse pressure gradient, the boundary layer flow is impeded and tends to show a reduction in velocity next to the surface. If the boundary layer does not have sufficient kinetic energy in the presence of the adverse pressure gradient, the lower levels of the boundary layer may stagnate prematurely. Premature stagnation of the boundary layer means that all subsequent airflow will overrun this point, and the boundary layer will separate from the surface. Surface flow which is aft of the separation point will indicate a local flow direction forward toward the separation point, a flow reversal. If separation occurs, the positive pressures are not recovered and form drag results. The points of separation on any aerodynamic surface may be noted by the reverse flow area. Tufts of cloth or string tacked to the surface will lie streamlined in an area of unseparated flow, but will lie forward in an area behind the separation point. The basic feature of airflow separation is stagnation of the lower levels of the boundary layer. Airflow separation results when the lower levels of the boundary layer do not have sufficient kinetic energy in the presence of an adverse pressure gradient. The most outstanding cases of airflow separation are shown in figure 1.26. An airfoil at some high angle of attack creates a pressure gradient on the upper surface too severe to allow the boundary layer to adhere to the surface. When the airflow does not adhere to the surface near the leading edge, the high suction pressures are lost and stall occurs. When the shock wave forms on the upper surface of a wing at high subsonic speeds, the increase of static pressure through the shock wave creates a very strong obstacle for the boundary layer. If the shock wave is sufficiently strong, separation will follow and compressibility buffet will result from the turbulent wake or separated flow. In order to prevent separation of a boundary layer in the presence of an adverse pressure gradient, the boundary layer must have the highest possible kinetic energy. If a choice is available, the turbulent boundary layer would be preferable to the laminar boundary layer because the turbulent velocity profile shows higher local velocities next to the surface. The most effective high-lift devices, slots, slotted flaps, BLC, utilize various techniques to increase the kinetic energy of the upper surface boundary layer to withstand the more severe pressure gradients common to the higher lift coefficients. Extreme surface roughness on full-scale aircraft, due to surface damage, heavy frost, etc., causes higher skin friction and greater energy loss in the boundary layer. The lower energy boundary layer may cause a noticeable change in uppercase CL max and stall speed. In the same sense, vortex generators applied to the surfaces of a high-speed airplane may allay compressibility buffet to some degree. The function of the vortex generators is to create a strong vortex which introduces high-velocity, high-energy air next to the surface to reduce or delay the shock-induced separation. These examples serve as a reminder that separation is the result of premature stagnation of the boundary layer, insufficient kinetic energy in the presence of an adverse pressure gradient. Scale effect. Since the boundary layer friction and kinetic energy are dependent on the characteristics of the boundary layer, Reynolds number is important in correlating aerodynamic characteristics. The variation of the aerodynamic characteristics with Reynolds number is termed a scale effect, and is extremely important in correlating wind tunnel test data of scale models with the actual flight characteristics of the full-size aircraft. The two most important section characteristics affected by scale effects are drag and maximum lift, the effect on pitching moments usually being negligible. From the known variation of boundary layer characteristics with Reynolds number, certain general effects may be anticipated. With increasing Reynolds number, it may be expected that the section maximum lift coefficient will increase from the higher energy turbulent boundary layer, and that the section drag coefficient will decrease, similar to that of the smooth plate. These effects are illustrated by the graphs of figure 1.27. The characteristics depicted in figure 1.27 are for the NACA 4412 airfoil. 4% camber at 40% chord, 12% thickness at 30% chord, a fairly typical, conventional, airfoil section. The lift curve shows a steady increase in lowercase CL max with increasing Rn. However, note that a smaller change in lowercase CL max occurs between Reynolds numbers of 6.0 and 9.0 million than occurs between 0.1 and 3.0 million. In other words, greater changes in lowercase CL max occur in the range of Reynolds numbers where the laminar, low-energy, boundary layer predominates. The drag curves for the section show essentially the same feature. The greatest variations occur at very low Reynolds numbers. Typical full-scale Reynolds numbers for aircraft in flight may be 3 to 500 million, where the boundary layer is predominantly turbulent. Scale model tests may involve Reynolds numbers of 0.1 to 5 million, where the boundary layer be predominantly laminar. Hence, that scale corrections are very necessary to correlate the principal aerodynamic characteristics. The very large changes in aerodynamic characteristics at low Reynolds numbers are due in great part to the low-energy laminar boundary layer typical of low Reynolds numbers. Low Reynolds numbers are the result of some combination of low velocity, small size, and high kinematic viscosity. Rn equals Vx over nu. Thus, small surfaces, low flight speeds, or very high altitudes can provide the regime of low Reynolds numbers. One interesting phenomenon associated with low Rn is the high form drag due to separation of the low-energy boundary layer. The ordinary golf ball operates at low Rn and would have very high form drag without dimpling. The surface roughness from dimpling disturbs the laminar boundary layer, forcing a premature transition to turbulent. The forced turbulence in the boundary layer reduces the form drag by providing a higher energy boundary layer to allay separation. Essentially, the same effect can be produced on a model airplane wing by roughening the leading edge. The turbulent boundary layer obtained may reduce the form drag due to separation. In each instance, the forced transition will be beneficial if the reduction in form drag is greater than the increase in skin friction. Of course, this possibility exists only at low Reynolds numbers. In a similar sense, trip wires or small surface protuberances on a wind tunnel model may be used to force transition of the boundary layer and simulate the effect of higher Reynolds numbers. Planform effects and airplane drag effect of wing planform. The previous discussion of aerodynamic forces concerned the properties of airfoil sections in two-dimensional flow with no consideration given to the influence of the planform. When the effects of wing planform are introduced, attention must be directed to the existence of flow components in the spanwise direction. In other words, airfoil section properties deal with flow in 2 dimensions, while planform properties consider flow in 3 dimensions. In order to fully describe the planform of a wing, several terms are required. The terms having the greatest influence on the aerodynamic characteristics are illustrated in Figure 1.28. 1. The wing area, capital S, is simply the planned surface area of the wing. Although a portion of the area may be covered by fuselage or nacelles, the pressure carryover on these surfaces allows legitimate consideration of the entire plan area. 2. The wingspan, lowercase b, is measured tip to tip. 3. The average chord, lowercase c, is the geometric average. The product of the span and the average chord is the wing area. Lowercase b times lowercase c equals capital S. 4. The aspect ratio, AR, is the proportion of the span and the average chord. AR equals lowercase b over lowercase c. If the planform has curvature and the average chord is not easily determined, an alternate expression is AR equals lowercase b squared over capital S. The aspect ratio is a fineness ratio of the wing, and this quantity is very powerful in determining the aerodynamic characteristics and structural weight. Typical aspect ratios vary from 35 for a high-performance sailplane to 3.5 for a jet fighter to 1.28 for a flying saucer. 5. The root chord, lowercase c sub r, is the chord at the wing centerline, and the tip chord, lowercase c sub t, is measured at the tip. 6. Considering the wing planform to have straight lines for the leading and trailing edges, the taper ratio, lowercase lambda, is the ratio of the tip chord to the root chord. Lowercase lambda equals lowercase c sub t over lowercase c sub r. The taper ratio affects the lift distribution and the structural weight of the wing. A rectangular wing has a taper ratio of 1.0, while the pointed tip delta wing has a taper ratio of 0.0. 7. The sweep angle, capital lambda, is usually measured as the angle between the line of 25% chords and a perpendicular to the root chord. The sweep of a wing causes definite changes in compressibility, maximum lift, and stall characteristics. 8. The mean aerodynamic chord, MAC, is the chord drawn through the centroid, geographical center, of plan area. A rectangular wing of this chord and the same span would have identical pitching moment characteristics. The MAC is located on the reference axis of the airplane and is a primary reference for longitudinal stability considerations. Note that the MAC is not the average chord, but is the chord through the centroid area. As an example, the pointed tip delta wing with a taper ratio of 0 would have an average chord equal to 1/2 the root chord, but an MAC equal to 2/3 of the root chord. The aspect ratio, taper ratio, and sweepback of a planform are the principal factors which determine the aerodynamic characteristics of a wing. These same quantities also have a definite influence on the structural weight and stiffness of a wing. Development of lift by a wing. In order to appreciate the effect of the planform on the aerodynamic characteristics, it is necessary to study the manner in which a wing produces lift. Figure 1.29 illustrates the three-dimensional flow pattern which results when the rectangular wing creates lift. If a wing is producing lift, a pressure differential will exist between the upper and lower surfaces, i.e., for positive lift, the static pressure on the upper surface will be less than on the lower surface. At the tips of the wing, the existence of this pressure differential creates the spanwise flow components shown in figure 1.29. For the rectangular wing, the lateral flow developed at the tip is quite strong and a strong vortex is created at the tip. The lateral flow and consequent vortex strength reduces inboard from the tip until it is 0 at the center line. The existence of the tip vortex is described by the drawings of figure 1.29. The rotational pressure flow combines with the local airstream flow to produce the resultant flow of the trailing vortex. Also, the downwash flow field behind a delta wing is illustrated by the photographs of figure 1.29. A tuft grid is mounted aft of the wing to visualize the local flow direction by deflection of the tuft elements. This tuft grid illustrates the existence of the tip vortices and the deflected airstream aft of the wing. Note that an increase in angle of attack increases lift and increases the flow deflection and strength of the tip vortices. Figure 1.30 illustrates the principal effect of the wing vortex system. The wing-producing lift can be represented by a series of vortex filaments which consist of the tip or trailing vortices coupled with the bound or line vortex. The tip vortices are coupled with the bound vortex when circulation is induced with lift. The effect of this vortex system is to create certain vertical velocity components in the vicinity of the wing. The illustration of these vertical velocities shows that ahead of the wing the bound vortex induces an upwash. Behind the wing, the coupled action of the bound vortex and the tip vortices induces a downwash. With the action of tip and bound vortices coupled, a final vertical velocity, 2 times lowercase w, is imparted to the airstream by the wing producing lift. This result is an inevitable consequence of a finite wing producing lift. The wing producing lift applies the equal and opposite force to the airstream and deflects it downward. One of the important factors in this system is that a downward velocity is created at the aerodynamic center, lowercase w, which is 1/2 the final downward velocity imparted to the airstream, 2 times lowercase w. The effect of the vertical velocities in the vicinity of the wing is best appreciated when they are added vectorially to the airstream velocity. The remote freestream well ahead of the wing is unaffected and its direction is opposite the flight path of the airplane. Aft of the wing, the vertical velocity, 2 times lowercase w, adds to the airstream velocity to produce the downwash angle, lowercase epsilon. At the aerodynamic center of the wing, the vertical velocity, lowercase w, adds to the airstream velocity to produce a downward deflection of the airstream 1/2 that of the downwash angle. In other words, the wing producing lift by the deflection of an airstream incurs a downward slant to wind in the immediate vicinity of the wing. Hence, the sections of the wing operate in an average relative wind which is inclined downward 1/2 the final downwash angle. This is one important feature which distinguishes the aerodynamic properties of a wing from the aerodynamic properties of an airfoil section. The induced velocities existing at the aerodynamic center of a finite wing create an average relative wind which is different from the remote freestream wind. Since the aerodynamic forces created by the airfoil sections of a wing depend upon the immediate airstream in which they operate, consideration must be given to the effect of the inclined average relative wind. To create a certain lift coefficient with the airfoil section, a certain angle must exist between the airfoil chord line and the average relative wind. This angle of attack is lowercase alpha naught, the section angle of attack. However, as this lift is developed on the wing, downwash is incurred, and the average relative wind is inclined. Thus, the wing must be given some angle of attack greater than the required section angle of attack to account for the inclination of the average relative wind. Since the wing must be given this additional angle of attack because of the induced flow, the angle between the average relative wind and the remote free stream is termed the induced angle of attack, lowercase alpha sub I. From this influence, the wing angle of attack is the sum of the section and induced angles of attack. Lowercase alpha equals lowercase alpha naught plus lowercase alpha sub I, where lowercase alpha equals wing angle of attack, lowercase alpha naught equals section angle of attack, and lowercase alpha sub I equals induced angle of attack. Induced drag. Another important influence of the induced flow is the orientation of the actual lift on a wing. Figure 1.30 illustrates the fact that the lift produced by the wing sections is perpendicular to the average relative wind. Since the average relative wind is inclined downward, the section lift is inclined aft, by the same amount the induced angle of attack, lowercase alpha sub I, the lift and drag of a wing must continue to be referred perpendicular and parallel to the remote free stream ahead of the wing. In this respect, the lift on the wing has a component of force parallel to the remote free stream. This component of lift in the drag direction is the undesirable, but unavoidable, consequence of developing lift with a finite wing and is termed induced drag, capital D sub I. Induced drag is separate from the drag due to form and friction and is due simply to the development of lift. By inspection of the force diagram of figure 1.30, a relationship between induced drag, lift, and induced angle of attack is apparent. The induced drag coefficient, capital C D sub I, will vary directly with the wing lift coefficient, capital CL, and the induced angle of attack, lowercase alpha sub I. The effective lift is the vertical component of the actual lift and, if the induced angle of attack is small, will be essentially the same as the actual lift. The horizontal and vertical components of drag are insignificant under the same conditions. By a detailed study of the factors involved, the following relationships can be derived for a wing with an elliptical lift distribution. 1. The induced drag equation follows the same form as applied to any other aerodynamic force. Capital D sub I equals capital C D sub I times lowercase q times capital S, where capital D sub I equals induced drag in pounds, lowercase q equals dynamic pressure in pounds per square foot, or lowercase sigma times v squared over 295, capital C D sub I equals induced drag coefficient, and capital S equals wing area in square feet. 2. The induced drag coefficient can be derived as capital C D sub I equals capital CL times sine lowercase alpha sub I, or capital C D sub I equals capital CL squared over pi times AR, or capital C D sub I equals 0.318 times the quantity capital CL squared over AR, where capital CL equals lift coefficient sine lowercase alpha sub I equals the natural sine of the induced angle of attack, lowercase alpha sub I in degrees, pi equals 3.1416 constant, and AR equals wing aspect ratio. 3. The induced angle of attack can be derived as lowercase alpha sub I equals 18.24 times the quantity capital CL over AR in degrees. Note: the derivation of these relationships may be found in any of the standard engineering aerodynamics textbooks. These relationships facilitate an understanding and appreciation of induced drag. The induced angle of attack, lowercase alpha sub I, equals 18.24 times the quantity capital CL over AR, depends on the lift coefficient and aspect ratio. Flight at high lift conditions such as low speed or maneuvering flight will create high induced angles of attack, while high speed, low lift flight will create very small induced angles of attack. The inference is that high lift coefficients require large downwash and result in large induced angles of attack. The effective aspect ratio is significant since a very high aspect ratio would produce a negligible induced angle of attack. If the aspect ratio were infinite, the induced angle of attack would be zero, and the aerodynamic characteristics of the wing would be identical with the airfoil section properties. On the other hand, if the wing aspect ratio is low, the induced angle of attack will be large, and the low aspect ratio airplane must operate at high angles of attack at maximum lift. Essentially, the low aspect ratio wing affects a relatively small mass of air and consequently must provide a large deflection, downwash, to produce lift. Effective lift. The induced drag coefficient, capital C d sub I, equals 0.318 times the quantity capital C L squared over AR, shows somewhat similar effects of lift coefficient and aspect ratio. Because of the power of variation of induced drag coefficient with lift coefficient, high lift coefficients provide very high induced drag and low lift coefficients very low induced drag. The direct effect of capital CL can be best appreciated by assuming an airplane is flying at a given weight, altitude, and airspeed. If the airplane is maneuvered from steady level flight to a load factor of 2, the lift coefficient is doubled, and the induced drag is 4 times as great. If the flight load factor is changed from 1 to 5, the induced drag is 25 times as great. If all other factors are held constant to single out this effect, it could be stated that induced drag varies as the square of the lift. Capital D sub I sub 2 over capital D sub I sub 1 equals the quantity L sub 2 over L sub 1 squared, where capital D sub I sub 1 equals induced drag corresponding to some original lift, L sub 1, capital D sub I sub 2 equals induced drag corresponding to some new lift, L sub 2, and lowercase q, or EAS, capital S, and AR are constant. This expression defines the effect of gross weight, maneuvers, and steep turns on the induced drag, e.g., 10% higher gross weight increases induced drag 21%, for G maneuvers cause 16 times as much induced drag, a turn with 45 degrees of bank requires a load factor of 1.41, and this doubles the induced drag. Effect of altitude. The effect of altitude on induced drag can be appreciated by holding all other factors constant. The general effect of altitude is expressed by capital D sub I sub 2 over capital D sub I sub 1 equals the quantity lowercase sigma sub 1 over lowercase sigma sub 2, where capital D sub I sub 1 equals induced drag corresponding to some original altitude density ratio, lowercase sigma sub 1, capital D sub I sub 2 equals induced drag corresponding to some new altitude density ratio, lowercase sigma sub 2, and L, capital S, AR, and V are constant. This relationship implies that induced drag would increase with altitude, e.g., a given airplane flying in level flight at a given TAS at 40,000 feet, lowercase sigma, equals 0.25, would have 4 times as much induced drag than when at sea level, lowercase sigma, equals 1.00. This effect results when the lower air density requires a greater deflection of the airstream to produce the same lift. However, if the airplane is flown at the same EAS, the dynamic pressure will be the same, and induced drag will not vary. In this case, the TAS would be higher at altitude to provide the same EAS. Effective speed. The general effect of speed on induced drag is unusual since low airspeeds are associated with high lift coefficients and high lift coefficients create high induced drag coefficients. The immediate implication is that induced drag increases with decreasing airspeed. If all other factors are held constant to single out the effect of airspeed, a rearrangement of the previous equations would predict that induced drag varies inversely as the square of the airspeed. Capital D sub I sub 2 over capital D sub I sub 1 equals the quantity V sub 1 over V sub 2 squared, where capital D sub I sub 1 equals induced drag corresponding to some original speed, V sub 1, capital D sub I sub 2 equals induced drag corresponding to some new speed, V sub 2, and L, capital S, AR, and lowercase sigma are constant. Such an effect would imply that a given airplane in steady flight would incur 1/4 as great an induced drag at twice as great a speed or 4 times as great an induced drag at half the original speed. This variation may be illustrated by assuming that an airplane in steady level flight is slowed from 300 to 150 knots. The dynamic pressure at 1% knots is 1/4 the dynamic pressure at 300 knots, and the wing must deflect the airstream 4 times as greatly to create the same lift. The same lift force is then slanted aft 4 times as greatly, and the induced drag is 4 times as great. The expressed variation of induced drag with speed points out that induced drag will be of greatest importance at low speeds and practically insignificant in flight at high dynamic pressures. For example, a typical single-engine jet airplane at low altitude and maximum level flight airspeed has an induced drag which is less than 1% of the total drag. However, this same airplane in steady flight just above the stall speed could have an induced drag which is approximately 75% of the total drag. Effective aspect ratio. The effective aspect ratio on the induced drag is the principal effect of the wing planform. Capital CD sub I equals 0.318 times capital CL squared over AR. The relationship for induced drag coefficient emphasizes the need of a high aspect ratio for the airplane which is continually operated at high lift coefficients. In other words, airplane configurations designed to operate at high lift coefficients during the major portion of their flight, sailplanes, cargo, transport, patrol, and anti-submarine types, demand a high aspect ratio wing to minimize the induced drag. While the high aspect ratio wing will minimize induced drag, long, thin wings increase structural weight and have relatively poor stiffness characteristics. This fact will temper the preference for a very high aspect ratio. Airplane configurations which are developed for very high-speed flight, especially supersonic flight, operate at relatively low lift coefficients and demand great aerodynamic cleanness. These configurations of airplanes do not have the same preference for high aspect ratio as the airplanes which operate continually at high lift coefficients. This usually results in the development of low aspect ratio planforms for these airplane configurations. The effective aspect ratio on the lift and drag characteristics is shown in Figure 1.31 for wings of a basic 9% symmetrical section. The basic airfoil section properties are shown on these curves, and these properties would be typical only of a wing planform of extremely high, infinite, aspect ratio. When a wing of some finite aspect ratio is constructed of this basic section, the principal differences will be in the lift and drag characteristics. The moment characteristics remain essentially the same. The effect of decreasing aspect ratio on the lift curve is to increase the wing angle of attack necessary to produce a given lift coefficient. The difference between the wing angle of attack and the section angle of attack is the induced angle of attack. Lowercase alpha sub I equals 18.24 times capital CL over AR, which increases with decreasing aspect ratio. The wing with the lower aspect ratio is less sensitive to changes in angle of attack and requires higher angles of attack for maximum lift. When the aspect ratio is very low, below 5 or 6, the induced angles of attack are not accurately predicted by the elementary equation for lowercase alpha sub I, and the graph of capital CL versus lowercase alpha develops distinct curvature. This effect is especially true at high lift coefficients where the lift curve for the very low aspect ratio wing is very shallow, and capital CL max and stall angle of attack are less sharply defined. The effective aspect ratio on wing drag characteristics may be appreciated from inspection of Figure 1.31. The basic section properties are shown as the drag characteristics of an infinite aspect ratio wing. When a planform of some finite aspect ratio is constructed, the wing drag coefficient is the sum of the induced drag coefficient. Capital CD sub I equals 0.318 times capital CL squared over AR, and the section drag coefficient. Decreasing aspect ratio increases the wing drag coefficient at any lift coefficient since the induced drag coefficient varies inversely with aspect ratio. When the aspect ratio is very low, the induced drag varies greatly with lift, and at high lift coefficients, the induced drag is very high and increases very rapidly with lift coefficient. While the effective aspect ratio on lift curve slope and drag due to lift is an important relationship, it must be realized that design for very high-speed flight does not favor the use of high aspect ratio planforms. Low aspect ratio planforms have structural advantages and allow the use of thin, low drag sections for high-speed flight. The aerodynamics of transonic and supersonic flight also favor short-span, low aspect ratio surfaces. Thus, the modern configuration of airplane designed for high-speed flight will have a low aspect ratio planform with characteristic aspect ratios of 2 to 4. The most important impression that should result is that the typical modern configuration will have high angles of attack for maximum lift and very prodigious drag due to lift at low flight speeds. This fact is of importance to the naval aviator because the majority of pilot-caused accidents occur during this regime of flight during takeoff, approach, and landing. Induced drag predominates in these regimes of flight. The modern configuration of high-speed airplane usually has a low aspect ratio planform with high wing loading. When wing sweepback is coupled with low aspect ratio, the wing lift curve has distinct curvature and is very flat at high angles of attack, i.e., at high CL increases very slowly with an increase in lowercase alpha. In addition, the drag curve shows extremely rapid rise at high lift coefficient since the drag due to lift is so very large. These effects produce flying qualities which are distinctly different from a more conventional, high aspect ratio airplane configuration. Some of the most important ramifications of the modern high-speed configuration are: 1. During takeoff, where the airplane must not be over-rotated to an excessive angle of attack. Any given airplane will have some fixed angle of attack, and CL, which produces the best takeoff performance, and this angle of attack will not vary with weight, density, altitude, or temperature. An excessive angle of attack produces additional induced drag and may have an undesirable effect on takeoff performance. Takeoff acceleration may be seriously reduced, and a large increase in takeoff distance may occur. Also, the initial climb performance may be marginal at an excessively low airspeed. There are modern configurations of airplanes of very low aspect ratio, plus sweepback, which if over-rotated during a high altitude, high gross weight takeoff cannot fly out of ground effect. With the more conventional airplane configuration, an excess angle of attack produces a well-defined stall. However, the modern airplane configuration at an excessive angle of attack has no sharply defined stall, but develops an excessive amount of induced drag. To be sure that it will not go unsaid, an excessively low angle of attack on takeoff creates its own problems: excess takeoff speed and distance and critical tire loads. 2. During approaches where the pilot must exercise proper technique to control the flight path. Attitude plus power equals performance. The modern high-speed configuration at low speeds will have low lift-drag ratios due to the high induced drag and can require relatively high power settings during the power approach. If the pilot interprets that his airplane is below the desired glide path, his first reaction must not be to just ease the nose up. An increase in angle of attack without an increase in power will lower the airspeed and greatly increase the induced drag. Such a reaction could create a high rate of descent and lead to very undesirable consequences. The angle of attack indicator coupled with the mirror landing system provides reference to the pilot and emphasizes that during the steady approach, angle of attack is the primary control of airspeed and power is the primary control of rate of climb or descent. Steep turns during approach at low airspeed are always undesirable in any type of airplane because of the increased stall speed and induced drag. Steep turns at low airspeeds in a low aspect ratio airplane can create extremely high induced drag and can incur dangerous sink rates. 3. During the landing phase where an excessive angle of attack, or excessively low airspeed, would create high induced drag and a high power setting to control rate of descent. A common error in the technique of landing modern configurations is a steep, low power approach to landing. The steep flight path requires considerable maneuver to flare the airplane for touchdown and necessitates a definite increase in angle of attack. Since the maneuver of the flare is a transient condition, the variation of both lift and drag with angle of attack must be considered. The lift and drag curves for a high aspect ratio wing, figure 1.31, show continued strong increase in CL, with lowercase alpha up to stall and large changes in CD only at the point of stall. These characteristics imply that the high aspect ratio airplane is usually capable of flare without unusual results. The increase in angle of attack at flare provides the increase in lift to change the flight path direction without large changes in drag to decelerate the airplane. The lift and drag curves for a low aspect ratio wing, figure 1.31, show that at high angles of attack the lift curve is shallow, i.e., small changes in CL, with increased lowercase alpha. This implies a large rotation needed to provide the lift to flare the airplane from a steep approach. The drag curve for the low aspect ratio wing shows large, powerful increases in CD with CL, well below the stall. These lift and drag characteristics of the low aspect ratio wing create a distinct change in the flare characteristics. If a flare is attempted from a steep approach at low airspeed, the increased angle of attack may provide such increased induced drag and rapid loss of airspeed that the airplane does not actually flare. A possible result is that an even higher sink rate may be incurred. This is one factor favoring the use of the no-flare or minimum flare type landing technique for certain modern configurations. These same aerodynamic properties set the best glide speeds of low aspect ratio airplanes above the speed for L/D max. The additional speed provides a more favorable margin of flare capability for flame-out landing from a steep glide path, low aspect ratio, low L/D max, low glide ratio. The landing technique must emphasize proper control of angle of attack and rate of descent to prevent high sink rates and hard landings. As before, to be sure that it will not go unsaid, excessive airspeed at landing creates its own problems: excessive wear and tear on tires and brakes, excessive landing distance, etc. The effect of the low aspect ratio planform of modern airplanes emphasizes the need for proper flying techniques at low airspeeds. Excessive angles of attack create enormous induced drag which can hinder takeoff performance and incur high sink rates at landing. Since such aircraft have intrinsic high minimum flying speeds, an excessively low angle of attack at takeoff or landing creates its own problems. These facts underscore the importance of a thread-the-needle, professional flying technique. Effective taper and sweepback. The aspect ratio of a wing is the primary factor in determining the three-dimensional characteristics of the ordinary wing and its drag due to lift. However, certain local effects take place throughout the span of the wing, and these effects are due to the distribution of area throughout the span. The distribution of lift along the span of a wing cannot have sharp discontinuities. Nature just doesn't arrange natural forces with sharp discontinuities. The typical lift distribution is arranged in some elliptical fashion. A representative distribution of the lift per foot of span along the skin of a wing is shown in Figure 1.32. The natural distribution of lift along the span of a wing provides a basis for appreciating the effect of area distribution and taper along the span. If the elliptical lift distribution is matched with a planform whose chord is distributed in an elliptical fashion, the elliptical wing, each square foot of area along the span produces exactly the same lift pressure. The elliptical wing planform then has each section of the wing working at exactly the same local lift coefficient, and the induced downflow at the wing is uniform throughout the span. In the aerodynamic sense, the elliptical wing is the most efficient planform because the uniformity of lift coefficient and downwash incurs the least induced drag for a given aspect ratio. The merit of any wing planform is then measured by the closeness with which the distribution of lift coefficient and downwash approach that of the elliptical planform. The effect of the elliptical planform is illustrated in Figure 1.32 by the plot of local lift coefficient to wing lift coefficient. Lowercase cl over capital CL versus semi-span distance. The elliptical wing produces a constant value of lowercase cl over capital CL equals 1.0 throughout the span from root to tip. Thus, the local section angle of attack, lowercase alpha naught, and local induced angle of attack, lowercase alpha sub I, are constant throughout the span. If the planform area distribution is anything other than elliptical, it may be expected that the local section and induced angles of attack will not be constant along the span. A planform previously considered is the simple rectangular wing which has a taper ratio of 1.0. A characteristic of the rectangular wing is a strong vortex at the tip with local downwash behind the wing which is high at the tip and low at the root. This large non-uniformity in downwash causes similar variation in the local induced angles of attack along the span. At the tip, where high downwash exists, the local induced angle of attack is greater than the average for the wing. Since the wing angle of attack is composed of the sum of lowercase alpha sub I and lowercase alpha naught, a large local lowercase alpha sub I reduces the local lowercase alpha naught, creating low local lift coefficients at the tip. The reverse is true at the root of the rectangular wing where low local downwash exists. This situation creates an induced angle of attack at the root which is less than the average for the wing and a local section angle of attack higher than the average for the wing. The result is shown by the graph of Figure 1.32 which depicts a local lift coefficient at the root almost 20% greater than the wing lift coefficient. The effect of the rectangular planform may be appreciated by matching a near elliptical lift distribution with a planform with a constant chord. The chords near the tip develop less lift pressure than the root and consequently have lower section lift coefficients. The great non-uniformity of local lift coefficient along the span implies that some sections carry more than their share of the load while others carry less than their share of the load. Hence, for a given aspect ratio, the rectangular planform will be less efficient than the elliptical wing. For example, a rectangular wing with an aspect ratio equal to 6 would have 16% higher induced angle of attack for the wing and 5% higher induced drag than an elliptical wing of the same aspect ratio. At the other extreme of taper is the pointed wing, which has a taper ratio of 0. The extremely small parcel of area at the pointed tip is not capable of holding the main tip vortex at the tip, and a drastic change in downwash distribution results. The pointed wing has greatest downwash at the root, and this downwash decreases toward the tip. In the immediate vicinity of the pointed tip, an upwash is encountered, which indicates that negative induced angles of attack exist in this area. The resulting variation of local lift coefficient shows low lowercase cl at the root and very high lowercase cl at the tip. This effect may be appreciated by realizing that the wide chords at the root produce low lift pressures, while the very narrow chords toward the tip are subject to very high lift pressures. The variation of lowercase cl over capital CL throughout the span of the wing of taper ratio equals 0 is shown on the graph of figure 1.32. As with the rectangular wing, the non-uniformity of downwash and lift distribution result in inefficiency of this planform. For example, a pointed wing of AR equals 6 would have 17% higher induced angle of attack for the wing and 13% higher induced drag than an elliptical wing of the same aspect ratio. Between the two extremes of taper will exist planforms of more tolerable efficiency. The variations of lowercase cl over capital CL for a wing of taper ratio equals 0.5 closely approximates the lift distribution of the elliptical wing, and the drag due to lift characteristics are nearly identical. A wing of AR equals 6 and taper ratio equals 0.5 has only 3% higher lowercase alpha sub I and 1% greater capital CD sub I than an elliptical wing of the same aspect ratio. A separate effect on the spanwise lift distribution is contributed by wing sweepback. Sweepback of the planform tends to alter the lift distribution, similar to decreasing the taper ratio. Also, large sweepback tends to increase induced drag. The elliptical wing is the ideal of the subsonic aerodynamic planform, since it provides a minimum of induced drag for a given aspect ratio. However, the major objection to the elliptical planform is the extreme difficulty of mechanical layout and construction. A highly tapered planform is desirable from the standpoint of structural weight and stiffness, and the usual wing planform may have a taper ratio from 0.45 to 0.2. Since structural considerations are quite important in the development of an airplane configuration, the tapered planform is a necessity for an efficient configuration. In order to preserve the aerodynamic efficiency, the resulting planform is tailored by wing twist and section variation to obtain as near as possible the elliptic lift distribution. Stall patterns. An additional effect of the planform area distribution is on the stall pattern of the wing. The desirable stall pattern of any wing is a stall which begins on the root sections first. The advantages of root stall first are that ailerons remain effective at high angles of attack, favorable stall warning results from the buffet on the empennage and aft portion of the fuselage, and the loss of downwash behind the root usually provides a stable nose-down moment to the airplane. Such a stall pattern is favored, but may be difficult to obtain with certain wing configurations. The types of stall patterns inherent with various planforms are illustrated in figure 1.33. The various planform effects are separated as follows. A. The elliptical planform has constant local lift coefficients throughout the span from root to tip. Such a lift distribution means that all sections will reach stall at essentially the same wing angle of attack, and stall will begin and progress uniformly throughout the span. While the elliptical wing would reach high lift coefficients before incipient stall, there would be little advance warning of complete stall. Also, the ailerons may lack effectiveness when the wing operates near the stall, and lateral control may be difficult. B. The lift distribution of the rectangular wing exhibits low local lift coefficients at the tip and high local lift coefficients at the root. Since the wing will initiate stall in the area of highest local lift coefficients, the rectangular wing is characterized by a strong root stall tendency. Of course, this stall pattern is favorable since there is adequate stall warning, the buffet, adequate aileron effectiveness, and usually strong stable moment changes on the airplane. Because of the great aerodynamic and structural inefficiency of this planform, the rectangular wing finds limited application only to low-cost, low-speed light planes. The simplicity of construction and favorable stall characteristics are predominating requirements of such an airplane. The stall sequence for a rectangular wing is shown by the tough grid pictures. The progressive flow separation illustrates the strong root stall tendency. C. The wing of moderate taper ratio, equals 0.5, has a lift distribution which closely approximates that of the elliptical wing. Hence, the stall pattern is much the same as the elliptical wing. D. The highly tapered wing of taper ratio, equals 0.25, shows the stall tendency inherent with high taper. The lift distribution of such a wing has distinct peaks just inboard from the tip. Since the wing stall is started in the vicinity of the highest local lift coefficient, this planform has a strong tip stall tendency. The initial stall is not started at the exact tip, but at the station inboard from the tip where highest local lift coefficients prevail. If an actual wing were allowed to stall in this fashion, the occurrence of stall would be typified by aileron buffet and wing drop. There would be no buffet of the empennage or aft fuselage, no strong nose-down moment, and very little if any aileron effectiveness. In order to prevent such undesirable happenings, the wing must be tailored to favor the stall pattern. The wing may be given a geometric twist or washout to decrease the local angles of attack at the tip. In addition, the airfoil section may be varied throughout the span such that sections with greater thickness and camber are located in the areas of highest local lift coefficients. The higher lowercase cl max of such sections can then develop the higher local lowercase cls and be less likely to stall. The addition of leading edge slots or slats toward the tip increase the local lowercase cl max and stall angle of attack and are useful in allaying tip stall and loss of aileron effectiveness. Another device for improving the stall pattern would be the forcing of stall in the desired location by decreasing the section lowercase cl max in this vicinity. The use of sharp leading edges or stall strips is a powerful device to control the stall pattern. E. The pointed tip wing of taper ratio equal to 0 develops extremely high local lift coefficients at the tip. For all practical purposes, the pointed tip will be stalled at any condition of lift unless extensive tailoring is applied to the wing. Such a planform has no practical application to an airplane which is definitely subsonic in performance. F. Sweepback applied to a wing planform alters the lift distribution similar to decreasing taper ratio. Also, a predominating influence of the swept planform is the tendency for a strong cross-flow of the boundary layer at high lift coefficients. Since the outboard sections of the wing trail the inboard sections, the outboard suction pressures tend to draw the boundary layer toward the tip. The result is a thickened low-energy boundary layer at the tips which is easily separated. The development of the spanwise flow in the boundary layer is illustrated by the photographs of Figure 1.33. Note that the die streamers on the upper surface of the swept wing develop a strong spanwise crossflow at high angles of attack. Slots, slats, and flow fences help to allay the strong tendency for spanwise flow. When sweepback and taper are combined in a planform, the inherent tip stall tendency is considerable. If tip stall of any significance is allowed to occur on the swept wing, an additional complication results. The forward shift in the wing center of pressure creates an unstable nose-up pitching moment. The stall sequence of a swept, tapered wing is indicated by the tough grid photographs of Figure 1.33. An additional effect on sweepback is the reduction in the slope of the lift curve and maximum lift coefficient. When the sweepback is large and combined with low aspect ratio, the lift curve is very shallow and maximum lift coefficient can occur at tremendous angles of attack. The lift curve of one typical low aspect ratio, highly tapered, swept wing airplane depicts a maximum lift coefficient at approximately 45-degree angle of attack. Such drastic angles of attack are impractical in many respects. If the airplane is operated at such high angles of attack, an extreme landing gear configuration is required, induced drag is extremely high, and the stability of the airplane may seriously deteriorate. Thus, the modern configuration of airplane may have minimum control speeds set by these factors rather than simple stall speeds based on capital CL max. When a wing of a given planform has various high lift devices added, the lift distribution and stall pattern can be greatly affected. Deflection of trailing edge flaps increases the local lift coefficient in the flapped areas, and since the stall angle of the flapped section is decreased, initial stall usually begins in the flapped area. The extension of slats simply allows the slatted areas to go to higher lift coefficients and angles of attack and generally delays stall in that vicinity. Also, power effects may adversely affect the stall pattern of the propeller-powered airplane. When the propeller-powered airplane is at high power and low speed, the flow induced at the wing root by the slipstream may cause considerable delay in the stall of the root sections. Hence, the propeller-powered airplane may have its most undesirable stall characteristics during the power-on stall rather than the power-off stall. Parasite drag. In addition to the drag caused by the development of lift, induced drag, there is the obvious drag which is not due to the development of lift. A wing surface even at zero lift will have profile drag due to skin friction and form. The other components of the airplane such as the fuselage, tail, nacelles, etc., contribute to drag because of their own form and skin friction. Any loss of momentum of the airstream due to power plant cooling, air conditioning, or leakage through construction or access gaps is, in effect, an additional drag. When the various components of the airplane are put together, the total drag will be greater than the sum of the individual components because of interference of one surface on the other. The most usual interference of importance occurs at the wing-body intersection where the growth of boundary layer on the fuselage reduces the boundary layer velocities on the wing root surface. This reduction in energy allows the wing root boundary layer to be more easily separated in the presence of an adverse pressure gradient. Since the upper wing surface has the more critical pressure gradients, a low wing position on a circular fuselage would create greater interference drag than a high wing position. Adequate filleting and control of local pressure gradients is necessary to minimize such additional drag due to interference. The sum of all the drags due to form, friction, leakage, and momentum losses, and interference drag is termed parasite drag since it is not directly associated with the development of lift. While this parasite drag is not directly associated with the production of lift, it is a variable with lift. The variation of parasite drag coefficient, capital CD sub p, with lift coefficient, capital CL is shown for a typical airplane in figure 1.34. The minimum parasite drag coefficient, capital CD sub p min, usually occurs at or near zero lift, and parasite drag coefficient increases above this point in a smooth curve. The induced drag coefficient is shown on the same graph for purposes of comparison since the total drag of the airplane is a sum of the parasite and induced drag. In many parts of airplane performance, it is necessary to completely distinguish between drag due to lift and drag not due to lift. The total drag of an airplane is the sum of the parasite and induced drags. Capital CD equals capital CD sub p plus capital CD sub I, where capital CD equals airplane drag coefficient, capital CD sub p equals parasite drag coefficient, capital CD sub I equals induced drag coefficient, or capital CD sub I equals 0.318 times capital CL squared over AR. From inspection of figure 1.34 it is seen that both capital CD sub p and capital CD sub I vary with lift coefficient. However, the usual variation of parasite drag allows a simple correlation with the induced drag term. In effect, the part of parasite drag above the minimum at zero lift can be lumped in with the induced drag coefficient by a constant factor which is defined as the airplane efficiency factor, lowercase e. By this method of accounting, the airplane drag coefficient is expressed as capital CD equals capital CD sub p min plus capital CD sub I over lowercase e. Capital CD equals capital CD sub p min plus 0.318 times the quantity capital CL squared over AR times lowercase e, where capital CD sub p min equals minimum parasite drag coefficient, capital CD sub I equals induced drag coefficient, and lowercase e equals airplane efficiency factor. In this form, the airplane drag coefficient is expressed as the sum of drag not due to lift capital CD sub p min and drag due to lift capital CD sub I over lowercase e. The airplane efficiency factor is some constant, usually less than unity, which includes parasite drag due to lift with the drag induced by lift. Capital CD sub p min is invariant with lift and represents the parasite drag at zero lift. A typical value of capital CD sub p min would be 0.020, of which the wing may account for 50%, the fuselage and nacelles 40%, and the tail 10%. The term of 0.318 times the quantity capital CL squared over AR times lowercase e accounts for all drag due to lift, the drag induced by lift, and the extra parasite drag due to lift. Typical values of the airplane efficiency factor range from 0.6 to 0.9 depending on the airplane configuration and its characteristics. While the term of drag due to lift does include some parasite drag, it is still generally referred to as induced drag. The second graph of Figure 1.34 shows that the sum of capital CD sub p min and capital CD sub I over lowercase e can approximate the actual airplane capital CD through a large range of lift coefficients. For airplanes of moderate aspect ratio, this representation of the airplane total drag is quite accurate in the ordinary range of lift coefficients up to near 70% of capital CL max. At high lift coefficients near capital CL max, the procedure is not too accurate because of the sharper variation of parasite drag at high angles of attack. In a sense, the airplane efficiency factor would change from the constant value and decrease. The deviation of the actual airplane drag from the approximating curve is quite noticeable for airplanes with low aspect ratio and sweepback. Another factor to consider is the effect of compressibility. Since compressibility effects would destroy this relationship, the greatest application is for subsonic performance analysis. The total airplane drag is the sum of the parasite and induced drags. Capital D equals capital D sub P plus capital D sub I, where capital D sub I equals induced drag, or capital D sub I equals 0.318 times the quantity capital CL squared over AR times lowercase e times lowercase q times capital S, and capital D sub P equals parasite drag, or capital D sub P equals capital CD sub P min times lowercase q times capital S. When expressed in this form, the induced drag, capital D sub I, includes all drags due to lift and is solely a function of lift. The parasite drag, capital D sub P, is the parasite drag and is completely independent of lift. It could be called the barn door drag of the airplane. An alternate expression for the parasite drag is capital D sub P equals lowercase f times lowercase q, where lowercase f equals equivalent parasite area in square feet, lowercase f equals capital CD sub P min times capital S, lowercase q equals dynamic pressure in pounds per square foot, or lowercase q equals lowercase sigma times v squared over 295, or capital D sub P equals lowercase f times lowercase sigma times v squared over 295. In this form, the equivalent parasite area, lowercase f, is the product of capital D sub P min and capital S, and relates an impression of the barn door size. Hence, parasite drag can be appreciated as the result of the dynamic pressure, lowercase q, acting on the equivalent parasite area, lowercase f. The equivalent parasite area is defined by this relationship as a hypothetical surface with a capital CD equals 1.0, which produces the same parasite drag as the airplane. An analogy would be a barn door in the airstream, which is equivalent to the airplane. Typical values for the equivalent parasite area range from lowercase q square feet for a clean fighter type airplane to 40 square feet for a large transport type airplane. Of course, when any airplane is changed from the clean configuration to the landing configuration, the equivalent parasite area increases. Effective configuration. The parasite drag, capital D sub P, is unaffected by lift, but is variable with dynamic pressure and equivalent parasite area. This principle furnishes the basis for illustrating the variation of parasite drag with the various conditions of flight. If all other factors are held constant, the parasite drag varies directly with the equivalent parasite area. Capital D sub P2 over capital D sub P1 equals lowercase f sub 2 over lowercase f sub 1, where capital D sub P1 equals parasite drag corresponding to some original parasite area, lowercase f sub 1. Capital D sub P2 equals parasite drag corresponding to some new parasite area, lowercase f sub 2. V and lowercase sigma are constant. As an example, the lowering of the landing gear and flaps may increase the parasite area 80%. At any given speed and altitude, this airplane would experience an 80% increase in parasite drag. Effect of altitude. In a similar manner, the effect of altitude on parasite drag may be appreciated. The general effect of altitude is expressed by capital D sub P2 over capital D sub P1 equals lowercase sigma sub 2 over lowercase sigma sub 1. Where capital D sub P1 equals parasite drag corresponding to some original altitude density ratio, lowercase sigma sub 1. Capital D sub P2 equals parasite drag corresponding to some new altitude density ratio, lowercase sigma sub 2, and lowercase f and v are constant. This relationship implies that parasite drag would decrease at altitude, e.g., a given airplane in flight at a given TAS at 40,000 feet, lowercase sigma, equals 0.25 would have 1/4 the parasite drag when at sea level, lowercase sigma, equals 1.00. This effect results when the lower air density produces less dynamic pressure. However, if the airplane is flown at a constant EAS, the dynamic pressure and, thus, parasite drag do not vary. In this case, the TAS would be higher at altitude to provide the same EAS. Effective speed. The effect of speed alone on parasite drag is the most important. If all other factors are held constant, the effect of velocity on parasite drag is expressed as capital D sub P1 equals parasite drag corresponding to some original speed, V sub 1, capital D sub P2 equals parasite drag corresponding to some new speed, V sub 2. Lowercase f and lowercase sigma are constant. This relationship expresses a powerful effect of speed on parasite drag. As an example, a given airplane in flight at some altitude would have 4 times as much parasite drag at twice as great a speed or 1/4 as much parasite drag at half the original speed. This fact may be appreciated by the relationship of dynamic pressure with speed twice as much V, 4 times as much lowercase q, and 4 times as much d. This expressed variation of parasite drag with speed points out that parasite drag will be of greatest importance at high speeds and practically insignificant in flight at low dynamic pressures. To illustrate this fact, an airplane in flight just above the stall speed could have a parasite drag which is only 25% of the total drag. However, this same airplane at maximum level flight speed at low altitude would have a parasite drag which is very nearly 100% of the total drag. The predominance of parasite drag at high flight speeds emphasizes the necessity for great aerodynamic cleanness, low lowercase f, to obtain high-speed performance. In the subsonic regime of flight, the ordinary configuration of airplane has a very large portion of the equivalent parasite area determined by skin friction drag. As the wing contributes nearly half of the total parasite drag, the profile drag of the wing can be minimized by the use of the airfoil sections which produce extensive laminar flow. A subtle effect on parasite drag occurs from the influence of the wing area. Since the wing area, capital S, appears directly in the parasite drag equation, a reduction in wing area would reduce the parasite drag if all other factors were unchanged. While the exact relationship involves consideration of many factors, most optimum airplane configurations have a strong preference for the highest practical wing loading and minimum wing surface area. As the flight speeds of aircraft approach the speed of sound, great care must be taken to delay and alleviate compressibility effects. In order to delay and reduce the drag rise associated with compressibility effects, the components of the airplanes must be arranged to reduce the early formation of shock waves on the airplane. This will generally require fuselage and nacelles of high fineness ratio, well-faired canopies, and thin wing sections which have very smooth uniform pressure distributions. Low aspect ratios and sweepback are favorable in delaying and reducing the compressibility drag rise. In addition, interference effects are quite important in transonic and supersonic flight, and the airplane cross-section area distribution must be controlled to minimize local velocity peaks which could create premature strong shockwave formation. The modern configuration of airplane will illustrate the features required to effect very high speed performance, low aspect ratio, sweepback, thin low drag sections, etc. These same features produce flight characteristics at low airspeeds which necessitate proper flying technique. Airplane total drag. The total drag of an airplane in flight is the sum of the induced and parasite drag. Figure 1.35 illustrates the variation of total drag with speed for a given airplane in level flight at a particular weight, configuration, and altitude. The parasite drag increases with speed varying as the square of the velocity while the induced drag decreases with speed varying inversely as the square of the velocity. The total drag of the airplane shows the predominance of induced drag at low speed and parasite drag at high speed. Specific points of interest on the drag curve are as follows. A. Stall of this particular airplane occurs at 100 knots and is indicated by a sharp rise in the actual drag. Since the generalized equations for induced and parasite do not account for conditions at stall, the actual drag of the airplane is depicted by the hook of the dotted line. B. At a speed of 124 knots, the airplane would incur a minimum rate of descent in power-off flight. Note that at this speed the induced drag comprises 75% of the total drag. If this airplane were powered with a reciprocating propeller-type powerplant, maximum endurance would occur at this airspeed. C. The point of minimum total drag occurs at a speed of 163 knots. Since this speed incurs the least total drag for lift-equal-weight flight, the airplane is operating at L/D max. Because of the particular manner in which parasite and induced drags vary with speed, parasite drag directly is the speed squared, induced drag inversely is the speed squared. The minimum total drag occurs when the induced and parasite drags are equal. The speed for minimum drag is an important reference for many items of airplane performance. One item previously presented related glide performance and lift-to-drag ratio. At the speed of 163 knots, this airplane incurs a total drag of 778 pounds while producing 12,000 pounds of lift. These figures indicate a maximum lift-to-drag ratio of 15.4 and relate a glide ratio of 15.4. In addition, if this airplane were jet-powered, the airplane would achieve maximum endurance at this airspeed for the specified altitude. If this airplane were propeller-powered, the airplane would achieve maximum range at this airspeed for the specified altitude. D. Point D is at an airspeed approximately 32% greater than the speed for L/D max. Note that the parasite drag comprises 75% of the total drag at a speed of 215 knots. This point on the drag curve produces the highest proportion between velocity and drag and would be the point for maximum range if the airplane were jet-powered. Because of the high proportion of parasite drag at this point, the long-range jet airplane has great preference for great aerodynamic cleanness and less demand for a high aspect ratio than the long-range propeller-powered airplane. E. At a speed of 400 knots, the induced drag is an extremely small part of the total drag and parasite drag predominates. F. As the airplane reaches very high flight speeds, the drag rises in a very rapid fashion due to compressibility. Since the generalized equation for parasite drag does not account for compressibility effects, the actual drag rise is typified by the dashed line. The airplane drag curve shown in Figure 1.34 is particular to one weight, configuration, and altitude in level flight. Any change in one of these variables will affect the specific drags at specific velocities. The airplane drag curve is a major factor in many items of airplane performance. Range, endurance, climb, maneuver, landing, takeoff, etc. performance are based on some relationship involving the airplane drag curve.